Hello? Hello? Anyone home? No, anyone home? Yes. Ah, Robert, hello. Is there anywhere where we could see a schedule? Alexei,
I can send it to you, Philip, if you send me an email.
made a lot of contributions, including publication, teaching, and student supervision. And we're glad that he's very enthusiastic and coordinates a lot of activities along with his teams, of course. And their hard work have made this conference possible. This is actually one of the first theoretical conferences in Shanghai Tech. We hope we'll have more, of course, in the coming future. We have to also special thanks to, in addition to Alexei, also to Yinan Zhou and Yifu Cai and Takaruba and Sravan Kumar for organizing this event. I wish everyone a successful and productive meeting. And we are honored to have distinguished scientists such as Professor Slava Mokhanov, Mikhail Chakoshnikov, Hello, Stella, Roboko, Frosch, and many other leading physicists in China and around the globe. And thanks again for joining us. I wish you a pleasant conference and also a pleasant stay in our university in Shanghai. Thank you.
Thank you very much, Mark, for this encouraging welcome. And now actually we have to come to the elements to the conference itself, but before this I will introduce a couple of practical details, okay? Here, Xian, did you put here PDF file? Ah, you put it just slow, sorry, you put it just slow. So, we are in Shanghai Tech and this is our campus, okay? This is where you enter on the east gate, and this is where you enter on the north gate, and this is where we are located. But the most important on this map is not this line is important. This line of canteen, these 3 dots in a row along the channel. There you go to have lunch in the break. And all of you who registered got lunch coupons. I just remind you that we cannot, here in the campus, we cannot accept cash or Alipay or WeChat. You just use these coupons, okay? So whoever not registered, please do it, okay? And whoever didn't pay registration fee, suddenly it's time to do it. And this map was sent to everyone, so I hope you will not be lost in the campus. And if you are lost or there are some questions, there are people like me with this green strap on the badge. You can ask us and we are happy to assist you. Okay, these are all our brave organizing team, students and other members. So there are some practical details about conference itself. Abhishek is in charge of taking PDF files. So please find either Abhishek directly or one of ourselves and upload PDF file in time. If you want to connect your laptop, tell us not the very last minute in a coffee break maybe. Wi-Fi is organized, you can use it. It's here, it's ID and password, yeah. Another important upgrade to the conference, we'll have conference dinner on July 3 on Wednesday at 6 p.m. It will be here in campus restaurant, all will be guided there. No worries about this. Yeah, and I see, and one more comment, the last moment comment, we decided some time ago to organize here poster presentations, and we sent them to those who brought here posters, but it will not be just poster presentation. We will select the best poster, and the best poster will be announced tomorrow, and this person who will get the best poster, he or she will be granted to give a talk at the end of the conference for 20 minutes. So potentially be prepared to give a talk, okay? Those who do posters. And tomorrow you will know who is it exactly. I think it's everything. Do you have any questions? Last minute questions before we go into actual talks? If there are no questions about this, you are welcome to find us with the green strap or whoever you know us. And now I pass the microphone to Yifu Cai, who is going to be chair of the first talk.
It's like you are lost in the program. Or I can yeah, your first speaker the presentation. Oh, I think that and oh, you're here. Okay, so yeah, first let us welcome Hai Hong An, Professor Hai Hong An from Tsinghua University. I guess well, sorry, I didn't even check what type it is, but I guess it's something like partial detection of a nucleotide, something like that. Okay, great. We have it in the private. How transition or switch transition occurred during the that's all.
Okay. Yeah, okay. Yeah. If you press on, it will go forward. Okay, thank you. Yeah, thank you very much for this very nice for the invitation, and it's actually I'm very happy to have this very good opportunity to present my recent works with my collaborators. So my main collaborators are Professor Lin Wang from University of Chicago and Kunfeng Li right now postdoc at Minnesota University, and Steve Zhou, who is right now a professor at Chongqing University, and also Xi Tong is right now a postdoc at Cambridge University, and Chen Yang and Bo Yesu, they are graduate students at Tsinghua University, and Han Wen is right now a student at University of Chicago. So I'm going to discuss consequences of phase transitions occurred during inflation. Yeah, okay, I think for this audience, I don't have to say too much about inflation. So basically inflation is a lot of people believe that inflation should happen, right? Should happen before the Big Bang universe, because inflation can solve the causality problem, can solve the flatness problem, and also the magnetic monopole problem, and the Okay. So that's over. Okay. So yeah, so it solves a lot of problems, right? And also it can give us a benefit, another benefit, which is a byproduct. It generates the seed of the large scale structure of the universe. And it is the large scale structure that we can observe today, right? But we know that to solve all the problems we mentioned in the previous slide. So to solve all these problems, we need at least 40 to 60 equals of inflation, right? But if we combine all the things we can observe CMB, we can observe large scale structures, like we can through this galaxy survey or MR survey, 100 centimeter survey. So if we put them all together, we can only observe about 10 equals, right? So we cannot observe all the part of the inflation. So that is actually a problem, right? So the problem is that we have a long time inflation, we can only observe a very small part. That means for the rest part, anything can actually happen, right? So the most successful inflation model till now is the slow roll inflation model, right? So in the slow roll, for slow roll inflation model to work, the excursion of the inflaton field is actually very large. So in most of the models, it is as large as the Planck scale, or even in some models, it is larger than the Planck scale, right? And so if it is larger than the Planck scale, we know there's another thing that must happen, is that the inflation must have an end. That means the inflaton field must couple to some other field, so that at the end of the inflation, the inflaton field, the energy of the inflaton field can be transferred into other field, right? Now, if you think that there's another field that couple to the inflaton field, that means that during the excursion of the inflaton field, the other field, we call it spectator field in this talk, the sigma. So during this talk, phi is the inflaton field and sigma is the spectator field. So you can see that if we introduce a very simple coupling between the inflaton field and the spectator field, right? So then during inflation, this inflaton field phi, the excursion or the change is as large as Planck's field. So that means that the parameters of the sigma field will change a lot. The parameters can be mass, like in this case, or coupling, like in this case, right? So, for example, in the first example, the mass of the sigma will change a lot. So, and maybe it has flip side, right? So if it flip side, it means something like a phase transition happens. And in the second example, the G is the spectator field, is something like a Younger's field, right? And so then during the evolution of the inflaton field, the Young's field can evolve from a weakly coupling regime to the strongly coupling regime, right? So then that also means the phase transition must happen. And the phase transition can be first order or second order or whatever else, right? So then this is the motivation for our work. So our strategy is the following. So we assume that during inflation, because the evolution of the infinite field is so large, so then the evolution will trigger a phase transition in the spectator sector. Okay. And then the phase transition of the spectator sector will lead to a lot of very interesting phenomena. So for example, it will introduce if the phase transition is like strong first order, it will produce gravitational waves. We call it primary gravitational waves. And if the phase transition is symmetry restoration, then the particles produced during phase transition can be stable. They can produce dark matter. And also, if the phase transition is symmetry breaking, it can introduce biological defects, right? We'll talk about that. And also, because there's an interaction between the inflaton field and the spectator field. And the spectator field during inflation is actually in a strongly interaction regime, right? So that will have a back reaction to the inflaton field. So that will induce a primordial non-Gaussian energy. And also that will induce primordial curvature, right? And the primordial curvature variation, if that is large enough, it will induce primordial fracture. And also, if it happens during the CMB mode, right? So then it can produce large-scale structure that can be observed today. And also, if it is large enough, once it comes back, it re-enters the horizon, it will produce secondary gravitational waves. So till now, we have done some studies about primary gravitational waves, dark matter, biological defects, and curvature perturbation, and the secondary gravitational waves. And the rest will be our future work. So this is the outline of the rest of my talk. So I will discuss first order phase transitions and second order phase transitions occur during inflation. And for first order phase transitions, I will discuss primary gravitational waves and dark matter production, curvature perturbation, and the secondary gravitational waves. And for second order phase transition, I will discuss mostly the topological defect production. So I will focus on domain walls, and then I will summarize. Okay, so now let's start from first order phase transition. Right. So why first order phase transition can happen? So first order phase transition just like we follow water, right? So it's just like this. So we have a potential field that depends on the inflaton field and the spectator. And then during the evolution of the inflaton field, the potential of the spectator field will be changed. So you can see that if we assume that there's a barrier between the full vacuum and the forced vacuum, then during inflation, during the evolution of the inflaton field, the shape of potential will be changed, right? And then the barrier becomes smaller and smaller. So once the barrier becomes smaller and smaller, it is more and more easier for the forced vacuum to tunnel into the true vacuum. So then it will produce bubbles. And when the bubbles apply with each other, they will produce gravitational waves, right? So this is just a standard story. And so the most important parameter for first order phase transition is actually beta. Beta is defined as a minus dS4 over dc. So what is S4? S4 is a bounce action that is produced by this little potential bounce. Okay. So the bounce action, once it is large, then it means that it is harder for the penetration or for the tunneling to happen, right? So when it becomes smaller during the evolution of the inflaton field, more and more bubble will climb, and then inflation will be then the phase transition will be finished. And this beta parameter also determines the radius of the bubbles, right, when they climb with each other. And they also it will also determine the frequency of the gravitational waves. Okay, so now let's talk about the primary gravitational wave that's produced during this bubble collision. So to calculate the gravitational waves, it's just like to calculate the electromagnetic waves, right? So we first linearize the Einstein equation, and then we want to first calculate the Green's function. So when we calculate the Green's function, the source is a delta function in both space and time, right? So and then we do a Fourier transformation. So basically, this equation just gives us this linearized Einstein equation in the Sitter space with instantaneous source, right? And so this is what we want to solve. So we already do a Fourier transformation, right? So in space. And so to solve it, it's actually very easy, right? But we want to solve it qualitatively. So what happened for Green's function is that because the source is a Green's function, so it must start at a fixed time, top right, right? And it starts also with a fixed phase. That is, it starts with h equal to 0, right? That is how we solve a Green's function. And then it oscillates with a decaying amplitude. Decaying is because the universe is expanding, right? So before this, before the mode exits the horizon, the amplitude will decrease. But what is special for the theta grid of a acceleratingly expanding universe is that there is a future event horizon, right? A future event horizon in conformal time is that means the conformal time has a finite end. So that means that this wave will oscillate, and then float onto a fixed value. Okay. Now what happened? What will happen for another mode with another frequency is that it will oscillate, and then float onto another value. Right. So then why is this important? It's because the value that it is frozen onto will become the amplitude when this mode re-enters the horizon, right? So it will be like this. So now we turn to the physical time, okay? So this x-axis is the physical time, and the y-axis is amplitude. So this part is actually during inflation. So you can see that you have a wave that oscillates and then frozen, okay, onto a fixed value. And then once it re-enters the horizon, what the inflation does is that it just erases the information of the phase, okay? And then the value, the mode frozen onto becomes the amplitude for later evolution. So then we know that this HF, which is the amplitude, oscillates with K, okay? Oscillates with the momentum. And so that is the reason that the power spectrum of the gravitational wave produced by a theta function source, that is actually oscillates with the momentum, okay? It oscillates with the momentum. So then we expect a multi-peak structure. So this is for a theta function source, that's for the Green's function. So to calculate the gravitational wave production for a real source, we actually need to convolute the gravity, the Green's function together with the real source, right? Together with the source. So then what happened? The source will always have a finite duration, right? So then what we expect is that, for example, for first order phase transition, the duration is actually measured by beta inverse, okay? And for the first transition to complete, beta must be larger than h, right? So then what we know is the following. So then for any, like for the mode that with the momentum that is larger than beta, then what we expect is that the oscillatory feature should be erased by the finite durations effect. But if the momentum is actually longer, if the momentum is smaller than beta, that means the wavelength is longer, then the source can still be seen as a theta function source, right? So then we expect that there's some like a multi-peak feature still retained, right? So even for the first order, for the real first order frequency. And then if the wavelength is very, very long, then once this mode produced, it is already outside the horizon. So then there's no chance for it to oscillate, right? So then the structure should be like this. So what really happens is that in flat space time for first order phase transition spectrum, gravitational wave spectrum, it's something like this. So the IR part is always it's always has a uniform behavior. It's model independent. And for the UV part, it's actually model dependent. So what the inflation does is that the inflation just distorts the IR part of the gravitational wave spectrum into a new IR part, right? It's no oscillation, and together with the oscillating part. And then squeeze the model dependent part into this new model dependent part, right? So from this sense, that means the prediction of the predicted spectrum of the gravitational waves that through the first order phase transition occurred during the inflation is some kind of universal, right? It always has an IR part and the oscillatory part. And the model dependent part actually suppressed. And so how large it is? It is actually not very small, so I will not go through the detail because of time limitation. So, but it is not very small. So to calculate this part is actually related to this part, right? So we can have a direct estimation. So the size of the strength of the gravitational wave measured by omega GW is actually proportional to omega r, which is the radical abundance of radiation. It's something like 10 to the minus 5. And then times h over beta times to the 6th power, right? And times delta rho over rho. Delta rho is the latent heat released during inflation, during the phase transition, and the rho inflation is the total energy density of inflation. So it's surprised by these two factors. And so if we are and for this new peak, it's actually surprised by the power by h over beta only to the fifth power. So if we are lucky enough, so if h over beta is something like 0.1, right, and delta rho over rho is something like 0.1, then the size of the gravitational wave can be as large as 10 to the minus 12, right? And so this is actually within the range of most of the future gravitational wave detectors. But if we are very unlucky, for example, if this h over beta is very small, right? So then the gravitational wave will be very tiny and we will never be able to observe it. But in this case, if someone asks me the question, right? So I will not present the detail. If someone asks me the question, I will go through the detail. So basically, in this case, for first order system, it happens during inflation. The value of h over beta is actually typically order like 0.1. Okay, so basically, we expect that if delta rho over rho is not too small, then we can observe this thing. Okay, so now what is the frequency, right? So we talk about size. The frequency is not an important issue. So the frequency in this case is actually determined by three parts. So one of them is actually the Hubble during inflation, right? So this peak, the physical momentum of this peak is actually the Hubble scale, okay? The Hubble scale. So then we need to count the redshifts, okay? And the redshifts can be separated by two factors. So one of them is the redshift after inflation, and the other is the redshift during inflation. And the redshift after inflation and sector strongly depend on the repeating temperature. And the redshift during inflation actually determined by the number of efforts that by the number of efforts before the end of inflation that the phase transition happened. Okay, so for example, we can show some example. That means that we can actually tune the frequency of the gravitational wave anywhere we like by changing the number of efforts that the phase transition happened. So basically, so for example, if we choose these parameters, we choose h roughly equal to 10 to the 12 GeV and delta rho over 0.3, right? Then we have this kind of parameter. So if we choose NE is the number of efforts before the end of inflation. If it is something like 38 before the end of inflation, then that means that the frequency falls into the right region that can be observed by pulsar timing array experiments. And if we change it to like 25 efforts before the end of inflation, or 21, right? It can be falls in the region by future space gravitational wave detectors. And if it is something like 15, then it is in the range of future terrestrial gravitational waves. Okay, so I think everyone's tired now, so that's using one slide to change gears, talk about dark matter very briefly. So this is just if we assume that the phase transition is similar to restoration, then the particle produced after the phase transition, after the Gauss collision will actually be stable, right? And then we can produce a lot of dark matter, right? And so we know that today's dark matter number is actually small, right? So the total, if the dark matter is as heavy as the proton, then the number density of dark matter is something like 10 to the minus 10 times the number density of the photon, right? So that means that we can have, there's some room for inflation to dilute the number density. So that means that actually the phase transitions can happen during inflation, okay? The production can happen during inflation. If we produce a lot, then after the dilution, we still have enough dark matter number density to explain what we observe today, okay? So this is actually the plot. So actually x-axis is the Hubble scale. So you can see that y-axis is the frequency of gravitational wave that the phase transition produced, assuming that we produce all the dark matter that we observe today. Okay, so now let's move to this curvature perturbation. So let's move to the curvature perturbation. So curvature perturbation is actually because of the backtrack segment. So it is actually very easy to see that the phase transition will induce a curvature perturbation. That is because we assume there's a direct interaction between the infiniton field and the spectator field. Okay, and then if you do a perturbation of the infiniton field, what you will have is something like this, right? You will have a term in this. So this potential will give you a term like partial V over partial phi naught delta phi, right? Okay, and this delta phi is actually the perturbation of the infiniton field. And then if you change gauge or whatever you want to do, right? So this delta phi will in the end become the curvature. Okay, and so now we can calculate the equatorial motion of delta phi. It will be something like this. And so what is special is that there is a source curve, and the source curve will be comprised by two terms. So the first term is actually from this direct interaction, as you can see, right? And the second term is a pure gravitation. and it is in our case, it is subdominant. And so what we need to do is that we need to calculate the source for the first order phase transition, and then we solve the Green's function for delta phi, and then we can calculate the curvature transition. So no one did this simulation before, so we use something like 1,000 cubic lattice to numerically solve this the evolution of the source. And the source is different from gravitational wave. That is because it is not the energy momentum tensor. It is actually partial V1 or partial phi naught. Right? It's something else. It is just not the same one. So we need to do the simulation. And so after we do the simulation, after we do the simulation of this S cube source, and then we put it into this differential equation. We solve the differential equation using the Green's function method, just like we solve the gravitational wave. And then from the delta phi, we can just calculate this curvature. Okay. And once we got this curvature region, we can calculate the 2-point spectrum of the curvature region. It's just like this. So because here we are aiming at some very large signal for the motivation I will discuss later. So we choose a very large, large beta h over beta naught. So basically a very small beta over h. So for example here, beta over h is around 5, 10, or 20, right? So we change those values and then we calculate we simulate the spectrum. So as you can see that here we already see some oscillation features. The reason is just the same as for the gravitational waves. And we also calculated this two-point function. And actually, the IR part of the two-point function is universal, just like before. And we can just numerically fit it, and it's close like just the frequency to cubic. And the size of the two-point function is like this. It is surprised by h over beta to the cubic power, and it's surprised by the R over rho to the second, and R is just like delta rho. It's the latent heat energy density during the phase transition. And we can also give a numerical result. And now let's talk about the secondary gravitational wave induced by this curvature transition. Right? And so this is actually follow the very long story, very large literature. A lot of people have started. So we just follow the standard technology, right? So basically, if you expand the Einstein equation to the second order, the gravitational potential itself will become the source for the gravitational wave. Okay, and so you can see that the source term has the bilinear is in the bilinear form of phi and cosine of gravitational potentials. Right? So follow the standard strategy because we already have the two-point function. So we can just calculate the gravitational waves, the secondary gravitational wave induced by first order phase transition during inflation, right? So until it turns out that the spectrums look like this, and the IR part again can be calculated analytically, right? So this is something like an semi-analytical formula for the IR part of the frequency. You can see that it goes like the frequency to the cubic power, but with all these log dependencies. And the log dependencies is because of the transfer function that is form factor F4 flex, right? So and if we neglect all the details, so let's go to the important part. The important part is that last year, so all the 4 post-Heilinger collaborations claim that they solve this Heiligenstadt curve, right? I think for this audience, I don't have to explain the Heiligenstadt curve. So they claim that they solve this Heiligenstadt curve. And even for nanograph, they have accumulated enough data so that they can actually publish the power spectrum of this gravitational waves, right? And you can see that the power spectrum is actually close, very close in the IR part, and the power is actually very close to 2. Okay, so then it is usually very hard for phase transition model to fit it because usually for phase transition model, the IR part just behave like 3. But in our case, it's not only 3, but together with all these log dependencies. So together with this log dependency, we can just use our model to fit very nicely the IR part of the spectrum. Right? Why only the IR part? Because the IR part of the UV part is actually very large, and so it is very hard to tell that what happened in this IR. In the UV part. Right? So we fit this result, and we use the toolkit provided by the nanograph collaboration, to calculate the relative base factor relative to the supermassive black hole binary model used in their field. okay? And it turned out that our model is actually better than other model, new physics model. For example, these models are scalar-induced gravitational waves through a delta function source, and this one is through a Gaussian source, and this is through a box source. And this is from bubble collision, and this one is from phase transition, but from sound waves. And then our model is actually here, right? So basically, it fits better thanks to this log dependencies. And yeah, and also we can do we can parameterize the IR part of our model with a two-parameter model. One of them is the amplitude, and the other is the center frequency. And so basically here, these two are the benchmark regions and shown here, right? So you can see that it can fit the IR part pretty well. And so we can have a comparison between the first order phase transition and have a comparison between the gravitational wave, the primary gravitational wave and the secondary gravitational. We can say that the primary gravitational, because you already asking question, why not we don't use primary gravitational wave, right? Why we only use secondary gravitational wave? So the reason is that in this case, the secondary gravitational wave is actually larger. The reason is that it is proportional to the curvature region. And the curvature regions are usually enhanced by the slow parameter, right? So although for the rest of the parameters, the factors, you can see that the primary gravitational wave is proportional to h over beta to the first power, delta rho or rho to the second power. And the secondary gravitational wave proportional to the h over beta to the sixth power, and delta rho or rho to the fourth power. Okay. However, it has an enhancement, which is the slow rho. It is also proportional inversely to the second power of the slow rho parameter. So this makes the secondary. So sometimes if the h over beta delta rho or rho is not too small, then the secondary gravitational wave can surpass can be stronger than the primary gravitational waves. So that's why in this case we use the secondary gravitational wave to feed the signal. And we already see that in the primary gravitational, the typical value for the primary gravitational wave, something like 10 to the minus 12. It is about 12 orders magnitude smaller than what we need to fit the nanogravity result. Okay, so now let me change to the second order phase transition, right? And the second order phase transition, so we know that usually for second order phase transition, it is very hard to produce large gravitational waves. But if there's a topological defect produced during the second order phase transition, then the things can be changed, right? So here we did some numerical simulation for secondary gravitational waves. And basically what we see that if we produce domain loss, and the domain loss without forming network, right? So usually we see domain loss produce gravitational wave. It's because domain loss can form network and then relation domains. But here it is different. Here the phase transition happens during inflation, right? And the phase transition happens during inflation, the domain loss will not form gravitational wave. Instead, what it will form is a static wall. Okay, and those static walls during inflation will actually produce gravitational waves. So what we did is the following. So we put a lambda filter type model. So basically, it's a lambda cycle model, right? So we assume that the mass of the spectator field can be changed because of the coupling with the inflaton field. And so once it fits time, so second order phase transition can happen, right? So and then after the second order phase transition happens, the size of the structure is actually determined by the Pivot-Duric mechanism. And the Pivot-Duric mechanism is actually determined by there's some parameter there, so which is the Pivot-Duric mass, and its inverse is the Pivot-Duric length. And it is Pivot-Duric length that determines the distance between the domain walls. Okay. And so the Pivot-Duric length, this Pivot-Duric mass in our case can actually be calculated very exactly in this model. It's determined by the slow roll parameter, right? Because it is triggered by the slow roll of the inflaton field. And so what we did is the following. So right after the phase transition, right? So the mass of the spectator field is actually tectonic, right? And because it is tectonic, the particle number can actually grows exponential. Okay, it can grow exponential. So you can see that we did some like numerical calculation. So just like this. So this y-axis is the occupation number of the certain mode, and the x-axis is the time. It's the physical time after the phase transition in the units of the Pivot-Duric time. So as you can see that it grew exponentially, and so because the occupation number is so large, So later we can treat the evolution classically. And so, yeah, so but after some while, when this interaction term becomes important, then this exponential growth just stops, right? But at that time, for the long wavelengths that we are interested in, we already collected a lot of occupation number, a very large occupation number, so that we can treat the evolution classically. So basically, what we did is that we can use this classical ensemble to mimic the quantum ensemble. And then we can just use the classical ensemble to randomly generate this sigma k, basically is the canonical coordinates, and pi k, which is the canonical momentum. Okay, so we randomly generate that as the initial condition, and then we put them into a still 1000 cubic lattice, and then to simulate the evolution and to get the domain walk to domain walks. So you can see that because of the expanding of the universe, the small oscillating structures are actually all released, right, by the expansion of the universe. But what in the end, only the topologically protected domain walls are left, and it becomes some static walls. That means the configuration doesn't change. So that is because the expansion of the universe is actually accelerating, right? And so then we can calculate the precisely structural part of the energy momentum tensor, and then use the Green's function method. We can just calculate the gravitational wave, right? And then so this is this plot shows the accumulated gravitational waves produced accumulated up to some certain number of effort after the phase transition during collision. So what we can do is that we can just turn off the gravitational wave production by changing delta rho to delta sigma to the absolute value of delta sigma. In this case, the production of domain walls will be turned off, right? So then we can compare these two cases. So here, these purple curves are with simulation with domain walls, and the green curves are the simulation without domain walls. So you can see that without domain walls, after the phase transition, the production of gravitational wave will be will decrease very soon, right? But with domain walls, it will be produced the production will last for another couple of number of efforts, and then the size of the produced gravitational wave will be actually much larger, right? Several order magnitude larger. And so here the production of gravitational waves is actually through static domain walls. We know that in flat space time, a static source cannot read it, right? But here we are in the theta space. The universe is fast expanding, right? So then in that case, the energy no longer conserves. So that means that even you have a static source that can read it. So basically the mathematical reason is the following. So the HF, which is the size of the gravitational wave amplitude, right? So can be written into the source of the gravitational wave convoluted by a kernel with something like a Green's function. And you can see that the kernel oscillates like this. So if we are in a flat space time, the kernel is a sine or cosine function. But here it oscillates like this. So then the last peak gives the largest contribution, right? So and then the contribution from different peaks never cancel with each other. So that's why here the production can be we can even with a static source we can still have a very large gravitational wave. And just like the first order phase condition, what we can do is that we can just calculate gravitational waves, and the frequency of gravitational wave is actually strongly depends on this on which number of effort the phase transition happens. Okay, and so this is the summary of my talk. So basically, our strategy is that we started the phase transition during inflation that triggered by the evolution of the inflation field, right? By the inflation field. So I hope I convince you that because the exertion of the inflation field during inflation is so large that the phase transition might be a common phenomenon happening during inflation, and it's a lot of interesting phenomenon that might be observed in future observations. And so in this talk, I talked about primary gravitational waves, dark matter production, and the topological defects and the curvature derivation induced secondary gravitational waves. So what we are currently working on is the primordial non-gaussianity, primordial black holes, and the large field structure that it can observe.
Well, you still asked a lot of time to question it, so yeah, please feel free to ask the question. Also. That's good.
So about this, maybe in your, if you, study the literature, it's kind of.
No, it's not finite because here we didn't assume it's a warm inflation model. And likely through the finite temperature effect, right? But in this case, we assume a cold inflation, right? So that the plasma effect is determined by the Hubble, right? So that is actually a small number.
How much change in potential? What is it?
Yeah, the potential is there by the interaction between the that is actually the very first slide, the interaction between the inflation. So inflation here work as a temperature. Huh?
No pursuit, no pursuit.
What do you?
The shapes of the potential.
The shape of the shape, here we didn't assume anything about the shape, the inflation potential. So we just assume it's low inflation. And so yeah, this is a spectator potential, potential for the spectator field. And so that because of the interaction between the inflation field and the spectator field, so the change of the inflation field will change the parameters of the spectator field. For example, the mass square, or maybe the copy, right? So that will trigger phase transition in the spectator effect. Yeah.
Regarding the production of primordial black holes, what is the amount of fine tuning, if any, that you have to produce enough black holes to take into account that matter?
We haven't gone through that yet. So right now we are mostly worried about how to treat this non-Gaussian energy effect. Yes, because you can see that here the curve information we produce is actually highly non-Gaussian, right? It's because it is from a classical source. A classical source will always have a hard part in the UV part, right? Because of energy conservation. So it's not a common, it will never be Gaussian. Yeah, so we are configuration of that part, so we haven't go through that findings here.
There are several different types of sources for the stochastic version from waves. I'm just wondering if we detect signals someday, is there a way to tell if the signal is from phase transition to inflation or is from some post-inflation effect?
Yeah, I think the feature, right? If it is from primary gravitational waves, then the feature will be the oscillatory feature. Here you can see that it has the synotic feature from if it is from the 1000 transition.
And this because the others post-inflation phase transition radiation of the state.
I think that I don't know. Yeah.
Any other questions? And so that you consider the detection of the gravitational waves from domain of, have you considered also other topological methods for this?
Yeah, we are doing the calculation now.
So which are the assets you are studying now?
Yes, so we already have preliminary results for cosmic streams and this also magnetic multiple.
And also, you can also consider fluxes or difference or just anything sense.
Yeah, we need to learn that first. Yeah, difference is sharp.
And another question, maybe it's a bit naive. Is there any condition that you can have that intensity of the secondary gravitational wave can be higher than the primary one?
So in the written one.
No, I mean, my second question, is there any condition?
Yeah, the data is that those parameters are not very small. So, I mean, I have a comparison slide. Yeah, this one. As you can see here, right? Here I have a comparison. So the secondary can be large because it's an enhancement from the fluoro effect. And into this factor, you can see that these factors they are also primary factors, right? So they have a larger power than the primary form. So if that means if H over beta is still very small, or third order is very small, then the secondary will be smaller.
Okay, so this distinction whether it's a primary or secondary, we cannot just say by looking at the intensity, but really have to understand the mechanism, how do we create it, yeah?
Yeah.
Okay. Thank you.
Any more questions? Sorry, I will give a chance to young one.
The primary version, second version, share the same, we have I wonder if promoting of energy and increase in this kind of experience.
Primordial non-causality. In this case, so right now we are starting the focus. So let me see. So there's the IR spectrum is actually a little bit different, right? Here it goes like I have cubic power, but here you can see that it has some additional features. I think it's from this from here, from this F2, this one, from this one. So it is not only F to the cubic, it is also has this logarithmic dependence.
Even the signal is getting that.
So very far IR. That part you cannot observe so because it's too small. So that part is supposed to like actually cubic. But here, for the part we can observe, it actually has a different feature because of this transfer function.
So, there are any common feature in the hybrid?
You know what part?
Hybrid.
High frequency part. No, I think they are, yeah, they are actually different. Like here, it goes like a very large power, or it's also what it is. So it just drops very fast. But the primary drops fast too, but it's relatively smaller, slower than.
Okay.
That's question from this side. Have you considered the type of anisotropic pattern visualization producer? Sorry, that would be something.
All right.
Have you considered anisotropy?
Anisotropy. Yeah, anisotropy. So it's a very something starting right for the large scale structure. So the anisotropy, so if this crystallization happens during the mode, at the time that the mode the CMB. Right? So then you can expect a large scale structure, something like large scale structure, and a large scale structural relations. And so if the crystallization is not very strong, if it is weak, so if you have a small h/beta value, then the size of the curvature relation is something like 10⁻⁹ is comparable to the CMB size. Then we can expect that maybe future CMB studies or maybe future 25 centimeter can be able to observe it. So yeah, if we have during the CMB,
I think one last chance for question here. Any more questions or guys are waiting for coffee now? If no more questions, then let's select the speaker again and. Now we'll have a break. We'll resume here in half an hour. Especially those who jet lagged will be taken to get some coffee. And those who didn't register, please do it, because without lunch coupons, you will have hard time to have your lunch. Okay?
Yes, we need to understand the mic arrangement. So which mics we want to, so this is one. And this two will be on the speakers, right? Not this one.
Some speakers just don't want the local.
Just you don't want, right? So forget about this thing. So everybody can hear everybody, so we can forget about these things. So maybe just this and this. So the last speaker actually came with these two mics, right? So
Just two mic, but there's a problem that online speaker cannot hear the questions because they can only hear the mic from here.
okay. Oh, but co-share guys does not.
Co-share can, but yeah, they can.
They can?
Yeah.
So both of the mics are working, right?
They got two mics. Yes.
No, forget about this. Oh,
This
okay.
for the questions. So co-share can hear this one.
Cannot hear this one.
Can hear this one, but the voice cannot pass Zoom to the online session.
It's okay. It's fine. It's for for local questions, right?
Uh-huh.
It doesn't.
Do you have another Bluetooth mic?
No, I can order one,
Um,
but it will
When will it be delivered?
tomorrow.
Tomorrow?
Yeah.
Well, then you can see. Just get a USB one, okay?
Yeah. This
Type C.
this thing, right?
No. Another this one, but with the USB plug, not the Type C plug.
Oh, I see. Then I have to sit with you.
Huh?
Then I have to sit with you to choose.
Okay.
Okay. So we need to do one thing. So it's
我个人做这轮呢，哪一个人就要做5个深蹲？我是也有听得到，有听得到，是吧？
I'm Roberto. Yes. So how does it working? Can I use this as a pointer?
So this is
Maybe I prefer because this is seen by everybody. Oh, the other one is seen only. I think I'll stay here. Probably. So this is to turn pages.
this is to count. So if you go down, then it will go forward. So if you let me see. Here is some other.
Well,
I think the sharing process is not top sharing.
Top sharing.
Share it again. Right. Yeah, now it's important. So move forward. The back. Yeah. Can you please put on this mic? Yeah, so there is
And if you want to use now, you can.
I think one of the complicated.
There, more video. Okay.
Everyone please sit down. So let's start our next session. So our first speaker is Professor Takashi from SITA. He's going to tell us physical running of couplings in quadratic right. Let's welcome.
So thank you very much, and to the organizers for bringing us here together, and in particular to Kutai and Alex for inviting me here. So I'm going to talk about this issue of running couplings. My content of my talk is in the papers in collaboration with Diego Bucho, who is a PhD student at CISA. He will get his degree later this year, and John Donahue. And the second paper was also with Gabriel Menez in Brazil. So the topic is various definitions of runnings of couplings. So mainly we're interested in questions of quantum gravity, and the issue of observables in quantum gravity is a difficult one. I will just talk about that type of observables that are typically used in particle physics. And then, so scattering amplitudes, basically. And for that, what the definition of running that is really useful is the first, what we call physical running. And that is based on defining the couplings in terms of some endpoint function. And in order to define the coupling, you have to fix some energy scale. And as you change the energy scale, the coupling will also change. And so we call that physical running. Then there are other definitions of running couplings. typically when you use the dimensionalization, you have to introduce, but also with the cutoff really, you have to introduce this dimension full parameter mu, and then you define couplings by taking derivatives of normalized coupling with respect to mu. We call that mu running, and in most familiar examples in particle physics, like Young's and lambda 5.4 and so on, you can freely interchange the physical running and the mu running. But that's not always the case, as we shall see. Then there is a totally different definition of running, which is non-perturbative, and that goes back to Wilson ideas. And in that case, what you do is you follow, you introduce some cutoff, which can be either ultraviolet or infrared, and you study the dependence of the couplings in the effective action as function of this cutoff. So again, there are various flavors of this. There's Wilson's renormalization group, there's Polchinski renormalization group, there's Vetri equation. So these are non-perturbative in contrast to the other two that apply to perturbation theorem. And it's they don't always give the same result. And since
Sorry, can I ask if that because I mean, does it be also in a non-perturbative sense, this first definition?
no, this is also perturbative, because the calculation of them is done.
But just that it can be considered.
In principle, yeah, in principle you can have it non-perturbative, but in practice.
But maybe so in the first case, you do it anyway to avoid large logarithms.
Yes, that is
But in that case,
yes,
in that sense.
yes, yes,
Example.
yes. So we chose a particular simple model where we compare all these definitions, and that is this shift invariant scalar field, and you see it has two kinetic terms, two derivative kinetic term and a four derivative kinetic term, and then there's an interaction which is four fields and four derivatives, and every field appears under derivative. So this is shift invariant. Now you can choose the field to be either dimensional full or dimensionless, depending whether you prefer this or that to be the really important kinetic term. But in either case, in this theory, there's a mass, which so for derivatives theory will have will propagate both two scalar particles, and one of them will be massless, the other will be massive. And the massive one is going to be a ghost. So M is the mass of a ghost. Here you can write Z2 as Z1 over M squared, and M is the mass of the ghost in this theory. And then there is an interaction scale, which is M over fourth root of G. G is the coupling appearing here. And we would like this scale to be much larger than the ghost mass in order to have a regime where the ghost can propagate and still be weakly interacting. So these are the three regimes of the theory. You're either below the threshold for the production of the ghosts, or you are above the threshold but still in the weakly coupled regime, or you are in a strongly coupled regime. Well, so now you can start looking at different endpoint functions in this theory. And the two-point function looks like that. You see that it is proportional to p squared. So it means that the Z1, the coupling with the kinetic term with two derivatives, gets renormalized. Z2 does not get renormalized. However, the renormalization of Z1 is by some you see there's this 1 over epsilon pole here, and there's a log of m squared over mu squared there. And so if you take the derivative with respect to mu, you get what I called earlier the mu running. So Z1 will run according to the definition of mu running, but it will not run in the physical sense because this logarithm doesn't depend on momentum. So this, you see, there's no log of momentum appearing there. So this is an example where there is mu running, but not no physical running in the sense that I defined. More interesting is a 4-point function, and you see it's very complicated. And what you see here is 1/3 4-point amplitude really, because then you have to add terms where ST and new parameters are permuted. So this is a function. You see the first term here is the tree level, S squared plus T squared plus U squared. And then there's some complicated expression. And I don't want to comment further on this other than showing that it's a very complicated. And this becomes only intelligible when you look either at very high energy or very low energy.
Epsilon, what is that?
Epsilon is the epsilon of dimensional regularization.
No, this is tree.
Sorry?
You said this is.
Oh, sorry, because I didn't look carefully. So the tree level term is of this form, but without the epsilon. And this is the quantum correction. Sorry, I didn't even look at it. So it is actually readable. Okay. So let's look at the low energy. Low energy means that ST and U are all lower than the mass square. Then you see at low energy, you would expect that the box by square term doesn't matter. And in that case, you can apply effective field theory reasoning. And you would expect to generate new interactions with of this form where you have d phi, d phi, d phi, d phi, and then it's an additional box. So this has 6 derivatives, and another term with box square. Yeah, so this will have 8 derivatives. In the effective field theory, such terms will come with the unknown coefficients G6, G6 prime, G8 prime. So if you define a renormalized coupling like that in terms of the variant, there's a 1 or epsilon pole here, and there's a log mu. Then the amplitude becomes reasonably simpler. This is now the whole thing. You see that this is the sea level, and then there's a loop correction. And none of the loop correction has S squared, T squared, U squared. No higher powers. So in fact, these terms are either 6 powers of energy or 8 powers of energy. And so they are terms of the type that I showed. Oops, sorry. They are correspond to terms of this form. And now, however, because this is now calculated from a fundamental theory, these couplings are not free. They are really functions of the coupling G that you put in the beginning. And you see here that G6 and G6 prime are fixed and they don't run, but the G8 and G8 prime are running couplings because they have here logarithms of the momentum. So E is here the energy at which you define your coupling. Okay. So from here you can read off the beta function, and G does not run. Neither do G6 and G6 prime. In G8 and G8 prime do run instead. So you may now compare this with the other methods of computing data functions. So if you use new type of definition, you will find that G runs, and this is not correct, it's not physical. If you use FRG, you get a more complicated expression that depends on momenta with powers. It goes like this. So this is now some power running, but you see that at least in this case, when k goes to 0, beta goes to 0. So in this case, the FRG, running with FRG reproduces the fact that G does not run in the extreme infrared. Now, more interesting still is high energy amplitude. Now, compared to the previous definition of G, we apply further finite renormalization, and we You know, the thing that, well, I come this way maybe a little bit. In this case, something that a priori is a bit unexpected happens. Namely, all those higher powers of momentum, the 6 power and 8 power, they disappear. And the amplitude remains is just a function of S and T and U squared. So you have here the tree level, and this is the loop correction. And so you can, the logs here appear with S, T, and U. And so you do have a physical running in this case. The beta function is written here. You get it from that formula. So this is a physical beta function. And actually, in this case, it agrees both with the new running and with the FRG. So in this case, at high energy, all the definitions agree, which is good. Oh, this is the matching of the low energy definition of G with the high energy definition. When you use a dimensional regularization, there is a you have to match two different definitions. This is the high energy definition, low energy definition is constant, and the matching is a step. The step itself is unphysical, obviously. Now, but this is not the problem because the physical running is always defined in the extreme regimes, either in the high UV or in the low infrared. The blue curve is the result of the FRG calculation. It looks more physical, but here in this intermediate regime, it's not really physical in the sense that it's not universal. It depends on details of how you compute running. It depends on details of the cutoff.
In understand that they make the matrix lineage for the together in the other side.
Well, maybe you wouldn't have this. This is you have a threshold here. You see, this threshold corresponds to the mass. This more or less this point is what the mass of the ghost is. Yeah. Without threshold, they would have logarithmic behavior.
Another question: what is the mass and you have the mass renormalization, right? You also have the field renormalization for the time.
Yes, but those things they don't run. I showed you the 2-point function. There's no physical running with 2-point function.
But this is the one loop plan.
This is all one loop here. Okay, so the lesson here is that you get running of or the same physical running of G is only defined in the asymptotic regions, and then there are various other regions where the different definitions of running do not agree. We only really agree in the extreme UV. Let me come to gravity, which is the story of greatest interest here. So we look at quadratic gravity, where you have Einstein-Hilbert action, plus also terms of quadratic in curvature, and usually they are parameterized like that by its which is curvature square and the Euler term. And very often this is reparameterized like that. It's 1 over psi is written as 1 over lambda times omega. So omega is the ratio of these two couplings. You find this, it's a historical in the literature. I call this the Planck mass square. So this theory is normalizable, and as you all know, I think, it propagates both the massless graviton and the massive spin 2 ghost and the massive spin 0 particle. And then, depending on the signs of lambda and psi, either the spin 2, the massive particles can be tachyons. So, in order to avoid tachyons, you want lambda to be positive and psi to be negative. So, in the lambda psi plane, there is only one quadrant where there are no tachyons. In the other 3 quadrants, you will have either the spin 0 or the spin 2 will be a tachyon. So many people have discussed the issue of the ghost. I will add nothing to that. And several also of you here in the audience. Now I want to focus on the issue of the running. So in order to compute the quantum corrections here, it's almost well, it is in gravity, you must use background field method. So you expand the metric around the background G bar, and H is the fluctuation. And this four derivatives Lagrangian will give rise to a Hessian, which is an operator like that. You have to make a particular gauge choice in order to have a nice operator like this. And with a particular gauge choice, you can eliminate all terms with four derivatives that are not merely a box squared. A priori, you get things like nabla nu, nabla rho, nabla sigma. You want to get rid of that. And you can with a gauge choice. So you remain then just with box square, and then two derivatives, one derivative, and no derivatives. You have this tensor structure in front of the box square term, which is a kind of a tensorial with functional renormalization. And you can then canonically normalize the field. So there's two parts here, the traceless and the you split H into trace free and trace parts, and you get different coefficients for those two parts. You redefine the fields with the square root of inverse of K, and then the operator becomes just box square with identity operator in front, which is nice. And so now the operator is just purely box square plus an object that I call B nabla nabla and the potential U. So just by dimensional analysis, V is proportional either to curvature or to the square plus mass, and it's proportional to gradients of the curvature of the background. And U is either the background curvature squared or its covariant derivative, its covariant Laplacian, or M Planck square R, or if you have cosmological constant. So there are different ways of using the background field method. One is to fix a particular background, for example, a sphere, and to compute your effective action in that case. Now that is not enough for us because on the sphere we would only get information about the R squared terms, but we would know nothing about Y squared. So we have to be more general. So we have to choose a background field that is general, and you can either choose the background fields to be a small perturbation of flat space, and then you can use Feynman diagrams, Fourier analysis, and so on. Or you can use the background to be completely generic, and that's the advantage that you have completely covariant expressions then. The second method is the one that was used in the first paper by Hubert on who were the first to try to compute the beta functions in this theory. So they showed the background that was small perturbation of flat. Then later, Fransky, Tseklin, and Barwinsky used the generic background and used heat kernel methods. So as I said, this is nice because you get covariant expressions. And since then, everybody has always used this second method. So then the divergences are, the logarithmic divergences are proportional to this heat kernel coefficient. And for a fourth order operator, it has the form written here, where you have the usual curvature of square terms, but also RV terms and V square terms and U. Now, if you are familiar with heat kernel of Laplacians, usually you will have U square here, the square of the potential. But for dimensional reason, because the operator is fourth order, here you get just a trace of U. Not stressing this because it's going to play important. This fact is important in memory. So the beta function that you get from this kernel calculation are written here. They have been established long ago, and they have been confirmed by many calculations over time, using very different methods, including the functional randomization group, for example, and both that's one group approximation and also going beyond that. So the important point is that if you analyze these data functions, you can, there is a region in lambda psi plane where the theory is asymptotically free. And so this has suggests that perhaps quantum gravity behaves a little bit like QCD, where you have a low free weakly coupled theory in the infrared. In the case of QCD, it's a theory of pions. In the case of gravity, it would be Einstein-Hilbert theory, gravitons governed by Einstein-Hilbert Lagrange. And you would have, again, a weakly coupled theory because there is this asymptotic freedom. In the middle, there could be some strongly coupled regime that may be difficult to analyze. So these are the 2 points. The low energy fixed point is at Einstein-Hilbert one. You have to expand the metric and rescale it with a square root of G. And in high energy, you take the H and you rescale it with the square root of lambda, and you get the free field. Given all this, the important question is what is the physics at these ultraviolet fixed points, whether it's Gaussian or not. And then can we flow from this ultraviolet fixed points to the infrared one? And I will focus on the first question here in the rest of the talk. So what is the physics? As I said earlier, one way of studying the physics is to study scattering amplitudes, and the shortcut to the to know the scaling behavior of scattering amplitude is compute renormalization group. But you have to compute the physical running in that case. And so the question then is whether those beta functions that I have shown are the physical beta functions in the sense that I defined. So in order to do that, we have to start computing some amplitude really. And to do that, we use methods from particle physics. And for that, we go back to the second way of using the background field, namely doing small fluctuations around flat space. So there is a first expansion, which is metric into a background plus a quantum field. And second, the background itself is split into a flat metric plus H bar, I call it. So this is not a quantum field, it's really a background field. Then the operator becomes the flat space Laplacian plus objects with 4, 3, 2, 1, and 0 derivatives. And now we have partial derivatives because we are doing flat space calculations. And these objects B, C, V, N, and U are polynomials in this background fluctuation, let me call it. The physical running of lambda and psi can be read off from the 2-point function, which in the effective action, it corresponds to terms that have the form curvature, log box curvature. So we need to compute this kind of things. And in Fourier space, it means you have to look at log of p squared. So we have to change the terms that have the logarithm of p squared in them. And so they are given by these 2 diagrams. The thick lines are the H bar propagators, the background propagators, and the thin lines are the quantum fields. The quantum field only circulates in the loops. And there are, for the 2-point function, you only have these 2 diagrams. You have a tadpole diagram and a bubble diagram. Now you know that, okay. So in the heat kernel, I stressed earlier, there is a term trace of U. So U is an interaction. You see in this, where is it? You have here the Hessian is, oops, sorry, the Hessian is H or H. So it's something quadratic in H, and then you have a function of H bar. And we look at just the term linear in H bar in each of these vertices. So U, N, V, and so on, they are vertices in this. And So each of these vertices here can be either U, N, B, or anything like that. So the fact that in the heat kernel you have trace of U appearing with power 1, it means that it is just this. Because here you would have, you see, you have two vertices there. It would give you U squared. But since you have in the heat kernel only U, it means that it comes from a tadpole. So this is the hunch that you have in the beginning, that those beta functions that were shown, that I showed you earlier, cannot be the physical beta functions because the tadpoles don't have momentum dependence. You cannot get log p squared. You see, you have momentum p here in this external line, and this diagram is independent of p. So the logs of p squared cannot come from that. Okay, so this was actually, John Donoghue has been saying for a couple of years, some of you may have heard him, that probably there's a problem with those beta functions. And the reason for that is what I just said here. And so the idea in the beginning was that maybe we just remove the tadpoles from the calculation and we get the physical beta functions. But if you do that, you will see that the expression that you remain with is not a covariant expression. So it will not be, actually, you see, since we're using this expansion of the background into eta plus h bar, you get the result of those calculations of time diagrams is some function of h bar. And you want this function of h bar to be the linearization of a covariant expression in the curvature d bar. And it isn't. If you remove the tadpoles, you get a non-covariant expression. So we were puzzled for some time. Eventually, we understood that there are other contributions on top of those that we had here. And these come from infrared logarithms. So there are, since the theory now has four derivative propagator, you know, four derivatives means that the propagators go like 1 over p to the 4. So having propagators that go like 1 over p to the 4 makes the theory more convergent in the ultraviolet. This is why the theory is normalizable. But it also brings with it the danger that you produce infrared divergences instead. So this theory, as it is, it does not really have infrared divergences because there is the Einstein term. The Einstein term is like a mass term for this high derivative gravity, and it fixes. I mean, it cures all the possible infrared divergences. However, when you look at the scattering amplitude at high energy, you look at momenta that are much higher than any masses. And usually, when you do that, you do the calculation, simply ignoring the masses. You put the masses to 0. If you do this in this theory, you will find infrared divergences. So for that, you have to cure the divergences, and you can do it either by infrared, by dimensional regularization again, or by putting a small mass in, and then taking the inner limit and the mass goes to 0. Either way, you will find that these infrared divergences contribute logarithms of momentum squared. So these terms by themselves are also not covariant, but when you add these infrared logs with the ultraviolet logs of p squared, they are an expression that is a linearization of a covariant expression in the background curvatures. And if you look at, instead of looking at log of p squared, in the, you just look at the log of mu squared, you will, those come only from the ultraviolet, and you will reproduce the old beta function. So you get new beta functions then, and here I compare the old and the new. So this is beta lambda and beta xi. They are not terribly different. The main difference is that now the beta of lambda doesn't depend only on lambda, it depends also on xi. Now, the qualitative features of the flow are determined by what I call the separatrices. You will see the picture in a second. And those are determined by the values of this parameter omega that I mentioned earlier, the ratio of lambda over psi. And in the older flow, omega had two fixed points that were both with a negative value. Whereas now you have one fixed point with negative omega and another with positive omega. So this reflects itself in the flow in the following way. In the old flow, well, the two separations are called S1 and S2. Here, they both have a positive slope, you see? This one and this one, they both have positive slope. Whereas in the new flow, S1 has still positive slope and S2 has negative slope. The region in yellow is the basin of attraction of the fixed point. So if you start anywhere in the yellow region, you will be attracted to the Gaussian fixed point. So it means that those points are asymptotically free. If you start somewhere else, you will be pushed to infinity. So here, the asymptotically free region, the first quadrant minus the tiny weight here. Whereas in the new flow, the asymptotically free region is the first quadrant plus a small weight in the fourth quadrant. Now, why does this matter? I told you earlier that the theory has tachyons, and the spin 2 is a tachyon on the left side of the quadrant, and spin 0 is a tachyon in the upper part of the quadrant of this plot. So the only region without tachyons is the fourth quadrant. And you see that previously there was no asymptotically free point in the fourth quadrant. So with the old beta function, asymptotic freedom comes together with tachyon. You must have a tachyon. Whereas with the new beta function, you can have asymptotic freedom and freedom from tachyons at the same time. So this is the main new feature of this calculation. Okay. So this is, in particular, this separatrix itself is an asymptotically free trajectory that lies entirely in the region So now, so the physics of this will have to be understood and studied better. And then here's my general summary. So we are used in theories with two derivatives to somehow confuse the new running and the physical running, because this always happens in the energy limit. But in theory, with four derivatives, this doesn't always happen. In particular, if there are infrared divergences, the two definitions of running may differ. And you see, this did not happen in the scalar theory. In the scalar model that I showed you, there were no infrared divergences. Two definitions of running in the high energy limit, they agree. But in the case of gravity, there are infrared divergences, and then the two definitions of running do not agree. So you have to be a bit more careful. So perhaps now we understand the physical running a little better. It doesn't still mean that we understand the physics of this fixed point at high energy very well, because it is true that the theory is asymptotically free, but still the interaction has four derivatives. And so it means that the amplitude grows like energy to the power 4. And you see there is a coefficient, the coupling in front goes like 1 over logarithm, which is good, but the fourth power of momentum completely swamps logarithm. So, as I said, the physics of this is not yet completely clear. Perhaps Bob will say something during this talk tomorrow. So, I think I can stop here.
Does the mu running solve the large logarithm problem even in for derivative theories or not?
Well, but are you interested in the large logs of mu? You see, you're interested in the large logs of p, really, not in the large logs of mu.
No, a large log of p. If the mu runnings of the large log of P problem.
If you want to solve the large log of P problem, you need to have to do the physical running.
So the answer is no.
Well, if they agree, then in a sense, you have solved. If the mu and physical running agree,
So if they
then
don't,
knowing that doing the
so if they don't agree, that means the new running does not solve
I
the.
would say not.
Yeah, I guess, the amplitude grows like e to the fourth, that means, strong coupling at high energy, right?
Yes.
So I wonder if you try to resound this contribution to see what happens, high energy, this doesn't sound possible.
I don't want to receive Bob. Well, so Bob has worked on this, and I think he's saying that you have to look at included cross sections, and then there are cancellations. And takes into behavior, but
These infrared,
sorry,
by the infrared divergences, you mean log of P squared or N squared?
yes, lots of P and squared.
Is this kind of the first example where these kind of logs appeared?
So to all of us, authors of these papers, this came as a surprise. But I met one person to whom it was not a surprise. So somebody had seen this kind of things before.
Is it always?
Not in gravity.
Was it a quadrilateral period?
Yes, it was so this was the Dumitru Bilencha here in Bucharest. And he had an example of this in a theory in 6 dimensions, that dimensionally reduced to 4. And somehow some extent, I think.
And as far as the e to the fourth by dimensional analysis, there would be a 1 over n with a large power as well. Yeah, or to get a cross section, you don't have any power to do that. Yeah, so that's another strange feature of these theories where n appears.
Even though it should be negligibly the same. Yeah. Yeah, I should say that another strange feature here is that, but no, okay.
Can you go beyond one room? Like that's just all the discussion is one room that
Yes. Yes.
would you expect high room and
Well, I think this problem is present probably also.
but wave function we thought will change the sign wave functions.
Oh, to change, well, perturbation theory, reliable, we would expect that it will not change sign.
Also for the Einstein gravity, when you go to the you mix with non-redundant. When you go pilot level, you have a new interaction term encounter which plays in one row and UV region. So you expect there's now I was supposed
Well, that's why we're studying high derivative gravity, because it is a normal.
Do you understand this mechanism of this strange phenomenon that you have the condensation of non-covariance of the contribution of penfolds against the contribution of infrared divergence, which are both separate, as you say, non-covariant? Because it would seem that if you perform all the calculation in an explicitly background covariant way, then I think you can discern the infrared divergence that would be actually covariant. So how comes that you have this? There is some mechanism of this condensation. Maybe there is some hidden symmetry practice.
Well, all I can say is we just do the calculation and we see what happens. We don't have a deep understanding of that, but of course it would be nice to see how we can reproduce this with the covariant method. So the last question.
So you're saying that about asymptotic freedom, you should make verdict based on the physical line? Why the physical line?
Sorry, if I say that
Around asymptotic freedom, you should make the final verdict based on the physical line.
yes, yes.
What was the motivation why the physical is better than the other one?
Like the name suggests.
That's what the name you choose, but we need more.
No, because really, no, sorry.
This was a historical request, because it was if the new runnings of the large value problem. If it doesn't, then you really have to transfer to Bayesian theory, you have to use the physical.
Yeah, maybe I didn't explain this well enough, but you can define randomization group, which is dependence of couplings on some parameters. Now, what is the physical meaning of that? Those parameters are unphysical. For example, the cutoffs, the mu, those are not physical other things. And so the dependence of random couplings from those parameters doesn't necessarily have a physical meaning. Now, you give the physical meaning if you use the physical definition of the random coupling, which is you define coupling as a function of a physical momentum. You do scan rate at some.
But this is one of the possible observable way. You have also
but this is the only one that is relevant in couplings. Let's put it like that. If you compute observables from the physical observables of particles, they are capturing. And that is all that matters in capturing.
Yeah, but
now I'm not denying that there could be other observables that are perhaps even more relevant in cosmology, where you could use where other definitions of running could be useful.
But that's why we would need the universality to prove.
Yeah, but as I said, I restricted myself to particle physics observables.
So yeah, let's somehow speak again. Can you hear me?
If you need to use this speaker, can
you hear me?
No, so you have to need to so it on fire for me to
So I have to put this other one
here. Just in front of your mouth.
Yes.
Okay. Yeah. So it's put it in the box.
Okay, great. So
This will.
okay, so our next speaker is Professor Alberto W. He is going to tell us about the quadratic gravity and the quantum cosmology.
Thank you very much. So, since my talk is about quadratic gravity, let me start from the very beginning by saying something about motivation for considering these terms. R square, R mu nu, R mu nu. You can also add other terms, but these are combinations of these two plus total derivatives. And the first motivation for me is that these terms are anyhow unavoidable generated by matter loops, such as this one, where dashed lines are scalar lines and double wave lines are external gravitons, but also other fields like vectors and bifermions, generic number and V and F, can contribute to the graviton propagator, giving some non-vanishing RG equations for the running of C2 and C2 prime. And here also I'm considering generic number of scalar fields NS with some nominal couplings given by this psi. So if you set them to 0, they anyhow generate radical corrections. And as Roberto said before, quadratic gravity is also renormalizable. The intuitive reason is that the UV theory is the most general dimensionless one. And
I'm adding on top of these two terms showed you before, the Einstein-Hilbert piece, LEH plus a cosmological constant, and the matter piece. Let me also rewrite those terms in terms of R square and W square, and these effective couplings F0 and F2. Another motivation for me for considering this theory is that the Higgs mass can be naturally smaller than the Planck mass. Here I'm using the Toff definition of naturalness. Physical quantity is naturally small when setting to zero leads to enhanced symmetry. And this ensures indeed that the quantum corrections respect the smallness of the physical quantity. The theory is also, as I said, renormalizable, so one can consistently compute the quantum corrections delta MH to the Higgs mass, and one finds this behavior of delta MH squared in terms of the couplings I showed you before, 0 and then F2, and by requiring the naturalness condition in terms of the Higgs mass MH, one gets that F2 has to be not larger than 10 to the minus 8. The small coupling, which is anyhow respected, the smallness of this coupling is anyhow respected by the RG equations. This is a particularization of a more general framework, which is called, which we call soft gravity. Einstein gravitational interactions increase with energy, and so they become out of control more or less at the Planck scale. But the idea here is softer gravity has some intermediate energy scale lambda g, much smaller than m Planck, such that the gravitational interactions become smaller and smaller when they pass this lambda g threshold. The gravitational contribution to the Higgs mass is this most general scenario is given by this expression here in order of magnitude by dimensional analysis, where Gm is the Newton constant, and requiring that delta MH is smaller than MH, the naturalness condition, we get a bound on lambda g, which is 11 GeV, which is compatible with the specific bound that we found before in the context of quadratic gravity. The reason for this is that the Higgs field acquires an approximate shift symmetry that protects MH. Okay, so
Einstein coupling grows with energy is a conjecture.
the Einstein coupling,
Einstein gravity coupling increase.
Yeah, the Einstein gravity does not fulfill this this conjecture.
But it could go to a fixed point, like asymptotic safety.
Yeah, but it needs to be softened, so it needs to become smaller and smaller. It needs to be going to zero, essentially. So you really need some asymptotic freedom behavior somehow. So not just asymptotic safety is not enough in principle. If it becomes strongly coupled.
Sorry, not enough for what?
For curing the Higgs mass naturalness problem, in principle, is not enough. So maybe with some extra mechanism, yes, but in principle. Okay. So this comes with a price, which is the fact that the theory, as Roberto mentioned, has a ghost, which is implied, which is a particular manifestation of the Strogansky theorem, Lagrangians that depend on the second derivatives have a Hamiltonian unbounded from below. And this manifests in quadratic gravity by expanding around the flat space. This one finds in this way a massless graviton, a scalar omega with a square mass roughly given by this expression here, and a massive spin-2 field with a abnormal cykinetic term, and a square mass given by this expression here, which is associated with the W square term. Another way to see this manifestation of the Strogansky theory is by linearizing the theory around flat space and computing also the Hamiltonian. For the graviton, we get quite normal Hamiltonian. Here, Q and P are the canonical coordinates. And for the ghosts, we get an abnormal one with an overall kinetic term. And here, the sum is over the Lizzie states. So, so we have to work on this problem. let me start with a perturbative reasoning. Let me split the metric as follows in a classical background GCL that solves the classical equations of motion and a quantum fluctuation H hat. The question is, can we avoid the possible Ostrogansky instabilities that are suggested by Ostrogansky theorem? Recall, first of all, that in the free field limits, the minus sign is not implying any instability because it cancels in the equations of motion in the free field limit. And also the effective theory tells us that at energies below M2, we should not find runaways, even if the abnormal graviton has an order 1 coupling. If we go at energies much below M2, there's a graviton couples, it's abnormal graviton. So this means that at the intermediate case, when F2 is between 0 and 1, we must have intermediate energy thresholds that go to infinity when you take F2 going to 0. So the weak coupling case, which is compatible with Higgs naturalness, must have an energy threshold that is much larger than F2. And in this case, we could see the effect of the abnormal graviton without runaways. This argument can be made precise as in classical quadratic gravity, and the whole cosmology can only involve energies below this threshold, as was proposed in, I proposed in 2019 and verified numerically by a number of authors. This is the argument. Let me skip it because I don't have time to go through it, but you can ask about this in the question and answer session. Let me go directly to the final answer for the threshold, which are different in the spin 2 sector and in the matter sector. In the first one, I get this threshold, which has to be imposed on the boundary conditions because we have control only on the boundary conditions, not on the dynamics of the field, which is given by the solution of the equation of motion. While in the matter sector, we have this other threshold. And for F2, very small, we see that the EM is much bigger than F2. What happens if we impose the naturalness condition for the Higgs mass, F2 at most of order 10 to the minus 8, we get E2 of order 10 to the minus 4 and Planck, and EM of order 10 to the minus 2 and Planck. So it is clear that inflation and the preceding epoch is the only stage of the universe that can provide us information about such high scale. So let's consider inflation. First of all, notice that the ghost is completely inactive in a cosmological Friedman-Robertson-Walker metric because this is conformally flat, and on this metric the value tensor vanishes exactly. So only perturbations that break homogeneity and isotropy may destabilize the universe. So this is the instability are related to the inhomogeneities and anisotropies. But we live in one of those patches where the energy scale of inhomogeneities that are called EI and anisotropies EA were small enough, pointed out by Linde in his chaotic inflation paper. And the conditions for neglecting the inhomogeneities in the equations of motion of the inflaton and the metric are those that are written here. These conditions justify the use of homogeneous and isotropic solutions to describe the classical part of inflation. And what happens is that the chaotic theory automatically ensures that the conditions to avoid runaway solutions are satisfied, at least in some very important models of inflation. Like I checked it explicitly for Starobinsky inflation, Higgs inflation, natural inflation, and other models. On the other hand, the further runaways above the energy thresholds that gives us an entropic rationale for a homogeneous and isotropic universe. So it really forbids, the theory really forbids to live on those patches that are not compatible with the chaotic inflation bounds that are written here. Okay, so let's consider now quantum fluctuations, because it's always possible that quantum fluctuations destabilize anyhow the universe. And let's look at H hat in particular. Okay, so first of all, renormalizability implies that the quantum Hamiltonian governing H hat is bounded from below, which is good. However, the space of states must be endowed with an indefinite metric. So we have to worry about probabilities, because if you just use the indefinite metric in the Born rule to calculate probabilities, you get negative probabilities, which doesn't make sense. Okay, so let's derive, however, the probabilities. Let's define any observable, any operator that has a complete set of states. We cannot define an operator to be observable to be Hermitian, because we don't know the inner product that we are going to use. If we use the indefinite inner product, we get negative probabilities. So it's not good to use hermiticity as a defining property of observable quantities. Let's use as a defining property the fact that it has a complete set of eigenstates. So any state psi can be decomposed as a linear combination of this eigenstate A. And one can show that the canonical operators Q and P in quadratic gravity have a complete set of eigenstates. Second, interpret this A as a state where a capital A, the observable, assumes certainly the value corresponding to the label A, which is the deterministic form rule. And then think like experimentalists do, prepare a larger number of times an experiment, and then send n to a very large number. Mathematically, we will send it to infinity. And this ensemble of experiments will be described by a large state, which is the direct product of this small psi state. Here, I'm also putting an overall normalization factor, which is defined here. Next, define a frequency operator, Fa, which counts the number Na of times there is the value A in the basis A1 AN for the capital psi state. This is the definition of Fa, defines Fa in the full space where psi n lives. And one can show now that in the limit n going to infinity, psi n becomes an eigenstate of Fa with eigenvalue precisely given by the Born rule, which is positive, and the sum over A of BA sum up to 1. So the theory is unitary. We just have to figure out what the inner product is to reproduce this Born rule. We can define a norm operator at this point, PA, by this condition here. And this condition define a PA that gives us a positive definite inner product defined by just inserting PA on the indefinite inner product, which is denoted by this psi 2 psi 1. And now, if you express the Born rule in terms of the PA inner product, you get the usual expression. We recover the full probabilistic Born rule, but expressed in terms of the positive norm, not in terms of the indefinite norm. Okay, so there is actually another unusual property that has to be used to quantize the theory, besides this that I've just said, which is the Dirac-Pauli quantization of canonical coordinates. In our definition, our A, an observable, is normal with respect to the A norm. This norm defined in terms of PA. So we can decompose A in terms of an Hermitian and anti-Hermitian operator with respect to the A norm that commute with each other. And so we can restrict to the case of observables that have a purely real and observables that have a purely imaginary spectrum. And what happens is that in quadratic gravity, there are also observables that realize the second possibility. This is the only option that indeed allows a Hamiltonian of this form with a minus sign to have a spectrum that is bounded from below and normalizable eigenfunctions at the same time. So what I said up to now was intrinsically perturbative. We started with a classical solution of equation of motion, and we also added on top of this small perturbations that are treated mechanically. So the question is, can we find a non-perturbative and also background independent formulation of quadratic gravity, formulation that is independent of this G classical GCL that I wrote before. The key idea here is to construct a theory with a consistent Euclidean path integral, which is anyhow required by describe our matter fields. And let me start first of all with simple Gauss coordinates, where the metric is given just by the dimensional metric Gij. And use the Strogarsky canonical method. In particular, I use one in which we choose Gij and Kij, which is proportional to the time derivative of Gij, as coordinates, and then the following fields as corresponding quantum momenta. The classical Hamiltonian density is then given in terms of the classical Lagrangian by the usual expression here. And H does depend on pi j, unlike M. L can be shown to be independent of pi j, but H then depends on pi j. But its dependence is on pi j is only given by this term here, which can be written in terms of Kij in this way. Now, if you use the standard quantization, you get a divergent Euclidean path integral because of this term here. The idea then is to Dirac-Pauli quantize Kij. So use the second option that I showed you in the previous slide to quantize Kij. And indeed, with an appropriate ordering, which can always be chosen, the transition amplitude from a state with the definite canonical coordinates Qi, the Euclidean time tau I, to a definite coordinate QF, Euclidean time tau F, in the presence of some external current, is given by this expression. And eta here means that I'm reversing the sign of all Dirac-Pauli variables, and this allows to construct a positive definite inner product. This is automatically a positive definite inner product. And C here is given by this expression, where the product is over all the Euclidean spacetime points. Delta V3 is the three-dimensional special volume element, and delta tau is the imaginary time element. And here, as E is the Euclidean action of quadratic gravity. And I'm using notation for these coefficients like before, because these alpha, beta, gamma, and lambda has to be considered pair parameters. They generically diverge when the cutoff is removed. We can also construct a generic formula for a generic gauge, which looks like this. Now F plays the role of a gauge fixing function, and psi play the role of the diffeomorphisms. So at the end, we have to construct a full metric measure, which is the previous one, which is invariant under three-dimensional diffeomorphisms. But now it also includes the delta psi, and can be shown to be invariant under four-dimensional diffeomorphisms. We can also study the convergence of the Euclidean path integral. And one finds that the convergence occurs if and only if these conditions are satisfied. And this is opposed to the case of Einstein gravity, where there are no region at all of the parameter space where the EPI converge. And this is also known as the conformal factor problem. As I said before, this alpha, beta, gamma, and lambda are their parameters. So they are not the physical parameters that have to be renormalized. So in particular, it is not possible to infer that the same conditions written here hold for normalized quantities in principle. One can, for example, not infer just from this that the cosmological constant in the theory needs to be positive, the physical one, not the pair one. Okay, one can also at this point derive the path integral for the generating function now of Green's functions. In the Euclidean case is given by this formula here. This factor here means that just that I have to divide this expression by the same expression with current J mu set to 0. And in the Lorentzian signature, I get this expression here. And notice that I've recovered the Fadder-Popov insertion, the usual Fadder-Popov insertion for the gauge fixing. And also, one recovers in this way perturbative calculations performing, expanding, say, around the Minkowski metric, like, for example, those performed by Bastelle and many others after him. But this formula also hold in the non-perturbative setup. We can also derive the effective action for quadratic gravity with this formalism. One starts from the expectation value of G mu nu in the presence of a physical energy momentum tensor that is still called J mu, and the expression is given here. And one can, at this point, construct the effective action by using the standard formula in terms of W defining this way in terms of Z. And with the effective action in our hands, we can compute the classical limit of the theory, h bar going to 0. In this limit, the path integral is dominated by a matrix satisfying these equations. And let me call the solution of this equation Gj, because it depends on the external energy momentum G mu. And one can show now that in the classical limit, gamma is given by this expression here, where Sren J is the starting action, but with renormalized coefficients, and computed in the corresponding Gj, namely the solution of this equation with S replaced by Sren. So the classical limit is described by the starting classical action with renormalized coefficients. So one can be puzzled at this point because the large distance spectrum of the quantum Hamiltonian is bounded from below, thanks to the presence of the Dirac-Pauli variables. And the reason why this happens is because the Dirac-Pauli quantization breaks the equality between the classical Hamiltonian that we call HC and this function of the canonical variables Q and P, which is obtained by taking this matrix element of the quantum Hamiltonian Hn divided by this inner product. In standard theories without the Dirac-Pauli quantization and in classical limits, H bar coincides with HC, but this is not the case in the presence of Dirac-Pauli variables. And the only thing that you can show in general is that the real part of H bar has to be bounded from below if the quantum Hamiltonian is bounded from below. Also, the metric remains real because the expectation value of a canonical variable is always real, regardless if it is a Dirac-Pauli variable or a standard variable. Okay, at this point, we can also apply this formalism to study quantum cosmology when one describes the universe through a quantum mechanical wave function as proposed by Hartle and Hawking. But they based their analysis on Einstein gravity, which has the conformal factor problem. So one advantage now is that we can describe quantum cosmology in a more rigorous way by using this consistent Euclidean path integral. Also, our fully quantum construction allows us to state that the configuration that leads to the smallest action corresponds to peaks in the wave function of the ground state and inhomogeneous anisotropic. While inhomogeneities and anisotropies lead to a larger action and are associated with excited states. This can be shown just by looking at the path integral that I derived before. And it is a property due to the fact that when you have inhomogeneities and anisotropies, you get a larger, when you have more of them, you get a larger value of W squared, the square of the Weyl tensor, which goes to 0 when you have no inhomogeneities and no anisotropies. There's also a nice relation with the finite action principle proposed by Lenz and Stelle, where they said that homogeneity and anisotropy of the universe can be motivated by the fact that the action has to be finite, and it is not if you have inhomogeneities and anisotropies in the initial time. Here, indeed, homogeneity and anisotropy is explained rather than postulated. It's a nearly homogeneous and isotropic patches that inflation can occur and observations can be eventually made. This can be shown at the quantum level by using the formulation I show you now at the quantum level with the path integral. And it extended the result that I discussed before, the constant of a classical theory, in relation with the chaotic inflation theory of Linde. So can we now, at this point, extract some observables and test the theory? So the first feature is that when the mass of the ghost M2 is larger than the Hubble rate during inflation H, we have no differences compared to GR. And this is reasonable because when M2 is larger than H, you have some sort of decoupling of the ghost. So let's focus on M2 smaller than H. We get these two differences. The tensor to scalar ratio R gets suppressed compared to the Einstein-Hilbert value RE by these suppressing factors. So in particular, models that are excluded by having a large RE, for example, quadratic inflation, become viable. And also there is an isocurvature mode which can fulfill the observational bounds, even in models that are excluded in Einstein gravity, corresponding to the scalar component of the abnormal graviton. The corresponding isocurvature power spectrum, called PB, is the same as the tensor power spectrum in Einstein gravity, but smaller by a factor 1/5, and this factor allows you to have models within the experimental powers. And indeed, this is the prediction in the plot of PB at two different scales, Q1 and Q2. And here is the 1 sigma region allowed at the 1 sigma level by Planck observations, and this is the 2 sigma level. So you see that you roughly need to have RE less than 0.1 to have agreement with data, rather than 0.04, which is more or less the current bounds for inflationary theories in Einstein gravity. We can also consider specific inflationary scenarios at this point. For example, scalar inflation, also known as Tarbinsky inflation, is a natural candidate because we have the R-squared term. Natural inflation is also an interesting possibility, because in this case, by definition, the inflaton is a pseudo-Goldstone boson, and so we have a naturally flat potential for the inflaton. And also, one can elegantly obtain a UV completion within an asymptotically free QCD-like theory. For natural inflation, we have this type of potential in terms of overall constant lambda to the 4th and another energy constant F dividing phi the inflaton here. We can also consider no-minimal coupling inflation, where the inflaton is a fundamental scalar with a no-minimal coupling to the Ricci scalar. Examples are from Higgs inflation and Hilltop inflation. But let me stick to the first two possibilities because of the reason that I said before. However, in all these possibilities, the conditions to avoid the Ostrogramsky instability are satisfied. I checked explicitly. So in the natural scalar inflation theory, we can describe inflation by looking at this parameter, rho, which is defined by this quantity. When rho goes to 0, you recover pure natural inflation. Where rho is large, you recover a pure scalar inflation, pure Stravinsky inflation. Here are some plots giving you the dependence on rho of the Hubble rate h and the constant lambda, which is obtained by requiring the power spectrum of the curvature perturbation to match the observed value. We can also vary f by fixing rho. The previous plot was by varying rho and fixing f. The important plots are these ones. 4 and 2 much larger than the Hubble rate h, and fixing some value of f, you see that you can enter the allowed region by taking a rho to be large enough. So in this case, and also by fixing rho and by f, the same result. You see that when the ghost is decoupled, you can enter the region by going towards Stravinsky inflation, which is what you expect, because Stravinsky inflation does agree with data. So when you go to Stravinsky inflation, eventually you enter the allowed region. But you can also enter the allowed region by using the ghost. So by taking M2 below the Hubble rate, you see that in this case, even if rho is not close to 0, so you're not close to Stravinsky inflation, you can enter the allowed region by this suppression factor for tensor to scalar ratio that I showed you before. Now, what about the cosmological constant at this point? You have some theory of quantum gravity. You might wonder if you can address the cosmological constant problems. One thing that I worked on recently was unimodular gravity, and unimodular, which is related to the cosmological constant problem. In unimodular gravity, one requires, by definition of unimodular gravity, that the space-time volume is not dynamical. Now, in the classical limit, you get, however, the same equations of motion of the theory without this modular constraint, independently on the theory one started with, as Roberto showed in 2017. But the only difference at the classical level is that the cosmological constant is an integration constant of the classical field equations in modular gravity. But this is not a physical difference. It's not something we can observe. The cosmological constant and vacuum energy, however, are independent in this construction. So modular gravity addresses the old cosmological constant problem that explains why such constant is not at least as large as the largest particle mass scale, because there is no reason it should be. Okay, since vacuum energy is decoupled from the cosmological constant. So one question is, can we distinguish unimodular and non-unimodular theories, at least quantum mechanically? Classically, we cannot. Can we do it quantum mechanically? The idea is to use the non-perturbative and background-independent quantum formulation of quadratic gravity I showed you before. And one can insert the following constraint delta function in the Euclidean path integral, where delta VE is some fixed non-dynamical volume form. And in the Lorentzian path integral, one can correspondingly insert this delta function, where delta V is the corresponding fixed non-dynamical volume form. We can also express this delta function in terms of a path integral over some field L, which plays the role of an auxiliary field. So we recover the auxiliary field formulation of modular gravity, where one adds to the action this integral here to enforce the modular condition. So at the quantum level, one can try to distinguish these two theories physically in an observable way. And the starting point is that this formulation of unimodular gravity does not break general covariance, actually, because what the delta function enforces the unimodular constraint in a generally covariant way. So one can take a standard Friedman-Robertson-Walker metric at the classical level, where A is a scale factor and U is conformal time. At the quantum level, one can choose conformal Newton gauge, where the metric is parameterized by these fields, the scalar perturbation psi and phi, tensor perturbations hij, which are constrained by these conditions, and the vector perturbations vi, constrained by these conditions. Now, in the modular theory, G is reduced to a C-number function. If you just work at the linear level, in perturbations where G is given by this expression, one gets this condition from unimodularity. Because the determinant of the metric has to be fixed equal to a C-number function of space-time. Okay, in the modular theory, by the delta functions I showed you before. Now, assuming that inflation is driven by a minimally coupled scalar field, one finds that psi goes to 0 in the super-horizon limit, so when A goes to infinity. So one consequence is that the curvature perturbation R acquires the same expression in Einstein gravity. So you get the same predictions for R and NS as in quadratic gravity without the modular constraint. So you get the same suppression factor for R, and NS is just like in Einstein gravity. However, the isocurvature mode B, which is present in quadratic gravity without the unimodular condition, decouples in unimodular gravity. And since future CNB observations may detect the power spectrum B, we can distinguish then unimodular and non-unimodular quadratic gravity at the quantum level. Now, unimodular gravity per se does not solve the new cosmological constant problem, which is why the cosmological constant has the observed value, even in this realization. So one can use at this point some anthropic reasoning. Let us consider the post-inflationary cosmology. Assume that the inflaton energy density is transferred as radiation to the observable sector, which includes the standard model fields, low energy. And this can be done in a number of explicit inflationary models like Starobinsky, natural Higgs inflation, and so on. Life is pretty impossible in both the inflationary epoch and the subsequent radiation-dominated epochs. As time passes, the radiation energy density decreases and the temperature drops. So a matter-dominated universe emerges in some epoch. Since the matter density, ρm, also decreases with time, eventually the energy density due to the cosmological constant that we call rho lambda surpasses ρm again. But in order not to violate the entropic bound, which was found by Weinberg in 1987, rho lambda should not be much larger than ρm. But since life takes time to develop, it's natural to find a scientific community in the latest possible epoch compatible with this bound, which is when we live. So the cosmological constant value is explained anthropically even in this construction, but by a multiverse made by different eras in a single Big Bang, a type of multiverse that was mentioned before, for example, by Banks. Okay, let me say a few words about decays and scattering now. The dp quantization of quadratic gravity and the appropriate Born rule that I showed you before lead to the following formula for decays and scattering processes. Here G is a ghost state and sigma is a non-ghost state, and pH0 is the norm operator corresponding to the free Hamiltonian. And for scattering, here sigma prime is also a non-ghost state. And U of t in both cases is a time evolution operator. At tree level, actually, this denominator can be dropped, just can be substituted by 1, and one recovers the standard quantum field theory formula. But at loop level, the denominators may play a non-trivial role. The relative corrections to the high energy behavior in quadratic gravity should, like other relative corrections, take into account the denominators in previous expressions, but we can consider just a three-level approximation, three-level with respect to the ghost coupling, in order to avoid taking into account these denominators. For example, by considering some three-level process like this. Now, at three-level, the limbic approach is recovered. Indeed, the ghost is unstable. PDK, now different from 0, can be proved perturbatively. This, of course, can be proved only because we have a sensible definition of probability, and therefore is not an asymptotic state. One obtains a lot of information about the high energy behavior of the theory already at tree level, as Strumi, Averme, and I showed in 2018. A classicalization effect takes place due to infrared effects in quadratic gravity. Super Planckian scatterings get downgraded to Planckian by radiating high gravitons and ghosts, which are weakly coupled and carry away the energy. So the theory becomes weakly coupled at high energy ultra-Planckian scales. And these are the conclusions. The classical runaway solution can be avoided even at energies exceeding the ghost mass. And runaways occurring above an energy threshold can explain homogeneity anisotropy for F2 over the 10 to the minus 8, which is the naturalness, the biggest naturalness value from Higgs naturalness. Interpreting probabilities as emergent from repeated experiments lead us to a way of quantizing the theory where all probabilities are positive and they sum up to 1. Furthermore, we have seen a non-perturbative and background formulation to a consistent Euclidean path integral, and we apply this to quantum cosmology. For F2 of order 10 to the minus 8, quadratic gravity leads to testable predictions for the inflationary observable. Also, it can suppress the value of tensor to Ceron ratio R and render viable many models that are ruled out in Einstein gravity. We consider a modular version of the theory, which has different predictions, addresses the old cosmological constant problem, and we have discussed some multiverse explanation of observed energy based on different time levels. Thank you very much.
Thank you, Professor. You say about the testable prediction of inflation, but to me they're not really classifiable because we don't, I mean, you just basically are in the sweet spot at Planck, but I haven't seen any characteristic signature of this theory over any other knowledge of inflation. On the other hand, when you have a higher derivative gravity, you tend to have a Shapiro-Kern advance, which is already strongly constrained by closer observations. So I would say that may be a problem.
Okay, so the first observation, I would say that you have the prediction of an isotopic moment in quadratic gravity, which is not present in any other theories that I've seen before. And the second point, one has to take into account that the theory does reduce to Einstein gravity at low energies. Low energies means just energies much below M2, which is for F2 over the 10 to the minus 8, the value compatible with the naturalness of the Higgs mass around 10 to the 10 GeV. But it means that not only at physical scale, but also at normal scales which are not microscopic, the theory is just Einstein gravity. So the only scenario arena where you can see differences that is observable is inflation, essentially.
Well, we usually want to look gravity, why was sleep C is equal to zero, or why is it equal to zero? But this is an contradiction with blending of light.
With what?
Blending of light.
Blending of light.
Yeah.
Why?
Because both potentials should be the same.
But they should be equal number.
But this is only true for scales above the gross mass. So if you are going to the beach mass.
No, if you will impose condition, determining which is requirements, then simply impose this space, and then you will get that phi is equal to psi for the gravitational potentials. But phi should be equal to psi if it is space correctly, because it's actually psi is the coefficient 2 in blending of light. When Einstein was.
The answer prediction of energies below the gross mass anyway. This was only for energies above the gross mass.
What do you mean gross mass? What is gross mass?
Gross mass is at 2, which is at 2 times the Planck mass. So it is roughly 1/10 the time really. So when you go below the scale, you get
Have a discussion during lunch.
so you get just a normal expression.
If you're right,
This is terrible.
yeah.
Okay, so let's have a discussion with that. Let's check our speaker again.
I can have a suggestion to you that if you want to have lunch, you follow people with green stuff, you are not sure where to go. Okay? And we are buying here again at Basel.
Well, next time remind me to turn to each other on that parable. Yeah. Just let me know, right? Yeah, it's fine. Parable. But I opened this because
Yeah, I'm providing the.
Yes, they're shortened tables. I sent you a link.
Well, actually.
Hello, hello. Hello, hello.
In the amount of my talking about just.
So the first speaker of this afternoon is Raptor.
Yeah, he sent me the slide. I
Okay.
don't know you. I believe you don't worry.
Okay. And the holster,
Sorry.
holster, the holster.
Most is already here.
Okay. Yes.
Hello, hello. Can you go to my laptop? There's a earphone. You can see, you can hear. Hello, hello, hello. Can you hear me? Can you hear me?
Me, please, pardon.
Still, nobody did any board presentation, but for safety, we have plenty here.
Okay.
Yeah.
So, yeah, what do you want? Yeah,
First, introduce yourself.
Hello? Hello? Hello?
外面这个音响是
Hello?
我在想，假设这个是一个线上的。
Hello? Hello?
Hello? Hello? Hello? Hello? Hello? Hello?
Hello? Hello? This is a test for online speakers.
Hello? 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 Hello?
Okay. Is the volume low? Is the volume good? Okay. The online speakers, and actually now since we plug this into this are the same device, we can allow them to speak.
So we don't need to do anything. So
Yeah,
if they just speak louder, then
yeah,
it will work.
yeah. But currently the Zoom they do not allow.
Yeah, because I like
unmute. But I asked him, he said he don't know how to do that.
No.
You know,
Okay, he knows. Without his laptop, you cannot do that because he is the host. He will do that. Don't worry. Let's check the other talks. Ah.
Can set the Zoom to English.
Just 8. Oh, yeah, it's okay. Yeah, don't open. Just close this slide. This is not.
This one?
Yeah, this one is the current. Yeah. So you should close it, otherwise I'll get confused. Just go outside.
No. Oh, I should project the timetable.
It's already 1:35, so we should not take it. So where now?
Actually, tomorrow I'll not be able to hear all the time.
Okay.
So,
Yeah.
we can write something very open with
Okay.
First, read whatever.
Yeah. So when you will not in the morning.
So we have to come back.
Very much.
Okay. I'll be there. I'll be here. Yeah, that's not really important.
Sorry, this one is a pointer?
Yeah.
You are the lecturer. You are the lecturer.
Yes, I am.
Yeah. So these are all the mines. So
you just go to the that all has what this
It's a mic.
so if you put it a bit outside, yeah, it's fine.
What it is?
Another one.
Another one?
Yeah.
So these are for two different streaming services. And this is for this local mine.
Local mic if you want. Or you can just speak louder.
Yeah. Little bit high side, like here.
I think it's fine. But this one should be fine.
Yeah, so it's fine. It's whatever it catches, it catches. Yeah, and you can put in any pocket.
Okay. That's the point. And close WeChat, of course.
Yeah.
Sorry,
You already closed it, but
Okay.
yeah. Oh, so it is in mute mode. So can you the receiver?
The box.
What's that?
It's in mute.
Okay, but maybe we have to wait. Wait a second. 2 minutes.
It's fine. It's okay. I put it on mute. So if you press this, then it will go forward.
I like this. Yeah. Okay. Okay.
Yeah. And this is the point.
The laser.
Point.
Okay. And I also can, if I can follow here, I mean.
Yeah.
You
If
can
I,
press this one.
if I press this, it's not doing, okay.
Yeah,
Maybe-
it's all.
We do want to put the local mic a little bit higher. This one.
Please,
This.
find like this,
Higher.
higher,
Yeah.
like this,
Try to speak something. Say something.
1, 2, 3.
Yeah. Sono il tuo chairman. Avverto quando sono il tuo chairman.
Sei il mio chairman.
Ti avverto quando mancano 5 minuti e poi.
Sì, ma io
Forse penso di farlo in, adesso non lo so, ma tipo 25 minuti.
Allora se così sarà, se
Nel
così
caso
sarà
ci sia,
non
dico.
vedrei niente.
Ok.
I think this one.
Welcome back. So, the speaker of the afternoon is Fabio Serdighi from Polytechnic of Milano. We're going to talk about scale-dependent gravity and Planck stars. Please.
So thank you very much. Thanks to the organizers for the invitation to give a talk here. And as the chairman said, I will tell you something about the Planck stars and the possibility to obtain a metric describing some properties of these objects. First, let me give a brief introduction to, well, you already probably not for this public, but a brief introduction to scale-dependent gravity or asymptotically safe gravity. In many quantum gravity approaches, the basic parameters that enter the action, such as Newton constant, electromagnetic coupling, cosmological constants, become scale-dependent quantities. So it seems that scale dependency at the level of effective action is a generic feature of ordinary quantum field theories. A typical scale-dependent effective action is gravitational action, is given by an object like this, which is essentially the Einstein-Hilbert action. Lambda is the cosmological constant, and here the G is instead of being just a number, is a function of a parameter, essentially representing the energy or the momentum scale at which you consider the theory. G of k and lambda of k are called running Newtonian or cosmological constant, running meaning that, of course, they are functions of k. For the problem that I'm going to consider here, I will consider lambda essentially equal to 0, so it's a local problem. I will talk about black holes. It is interesting, it is useful to introduce a dimensionless Newton constant defined in this way. And then you can write down an evolution equation for these scale-dependent quantities, differential equation of first order differential equation for the G of k, which can be integrated and gives the dependence of the running Newton constant, dimensionful running Newton constant on the energy scale. And this omega tilde parameter, essentially, from the mathematical point of view, is just the integration constant of the previous first order differential equation. Immediately, we see that we have a deviation from standard physics at high energies. When k goes to infinity, then or very large, then j of k is going to 0. As on the contrary, we recover classical space-time for small at low energies, so to say. Obviously, the sign of this parameter omega tilde is crucial for the physics of the theory. In the case of the so-called asymptotically safe gravity, omega is assumed to be positive, so that gravity can be asymptotically safe from divergences. Essentially, it becomes weaker and weaker for growing case. If instead we consider omega tilde negative, then immediately you see that you can have a divergence of the g of k for when k assumes the value close to the Planckian scale. So usually when omega is positive, the theory is called ASG, asymptotically safe gravity. Otherwise, more general, you talk about scale-dependent gravity.
This omega is the parameter of any vehicle.
Sorry?
I say the omega. It is the parameter of any vehicle quantity.
Essentially, omega is at this level is the integration constant of this differential equation here. So in case of asymptotically safe gravity, omega is through several arguments, you see that omega should be positive. Actually, you want it to be positive in order to have weak gravities at high energies. But in this particular approach, we consider the possibility to have also an omega negative. Another fundamental step in order to arrive to write a metric for a black hole, a space-time metric, black hole metric is to link k with a radial coordinate, and these usually this expression here is the one introduced by for the first time by Bonanno and Reuter in 2000. K of R in this case is a kind of modified proper distances. You see that for large R is going like H over R. And the gamma, the new parameter gamma here can be somehow fixed at least for some with some general relativistic argument to be equal to 9/2. But the numerical value is not so important. We just assume gamma positive. If you consider now, you go to consider the global G, then the G becomes a function of R. And you see that clearly there are quantum effects, so to say, incorporated in this expression. Here you have the typical H bar and Planck length in this expression. In scale dependent or also in asymptotically safe gravity, the approach in order to get scale dependent solutions in Newtonian or general relativistic solutions, people replace everywhere Newton constant G0, the numerical Newton constant, with the running constant G of R. For example, we can consider a spherically symmetric Lorentzian metric with a lapse given by the standard Schwarzschild, the standard Schwarzschild metric, and replacing G with G of R here gives to you directly this form of this the lapse. It's an interesting metric, this, because you have well, you can see two important limits for large R, and which means low energies. You recover the Schwarzschild metric. On the contrary, at small r, so at very high energies, you get a singularity free at the core. The usual singularity of Schwarzschild is completely cured, so to say. And for gamma positive, you have an expression like this, which is according to the sign of this parameter, omega tilde gamma is can be a de Sitter or an anti-de Sitter core, so to say. In the particular, but very particular case of gamma equals 0, then still it's a singularity-free metric at the core, at least at the core, and then it's called conic singularity, this expression here. We can define, as I said, by replacing the numerical Newton constant with the running coupling G of R, it is possible to write down a scale-dependent modified Newtonian potential, which has this expression here. And again, for large R, you can expand in R and see the corrections to the standard Newtonian potential, depending directly on H bar, so the quantum corrections. We see from here that the correction predicted by this approach are this scale-dependent or asymptotically safe approach are of genuine quantum nature because of the presence of H bar. And then there is, of course, the problem of how to fix the omega tilde parameter. Usually people in the asymptotically safe gravity community compared this potential with the quantum corrected potential, Newtonian potential obtained by Donahue, Kripovich, Shapiro, and other people, considering general relativity as an effective field theory at low energy. If you do that, then you can fix. This is the result of the calculation of Donahue, and as I said, different other authors, Kripovich, Freub, and others. Essentially, you get a correction on the first order here, on the first order in H bar, a positive, an expression of this kind. The last term is a true long distance quantum effect, linear in H bar. And we are neglecting here post-Newtonian classical correction terms. Then by comparing these with the potential obtained from the scale-dependent theory, the scale-dependent formula that I showed you before, you can fix, comparing the two orders, omega tilde as having this value here. Actually, the precise numerical value is not so, perhaps not so important. For example, a different calculation performed by Ilya Shapiro gives a different numerical value of this omega tilde, but the important message is the fact that this omega tilde can also be negative, at least, can also be considered as negative. As I said, the sign of omega is crucial for the physics of our system. As I said, gravity is asymptotically safe only when omega tilde is positive. In case of, and of course, if omega tilde is positive, you have a singularity-free metric. On the contrary, if omega is negative, the G of k can diverge. And as I said, several different calculations performed by these different authors in different years, they all point towards a possible negative values of omega. If we consider now the metric that I presented you before with this omega negative, then you see immediately that the denominator can develop zeros. And so the metric can have singularities, and actually it is possible to show that this cubic equation has one single positive root at R0 greater than 0 for any reasonable values of the variable. Of course, R should be positive, gamma is assumed to be positive, and positive masses. And these singularities an actual essential singularity, so to say. If you compute the Kretschmann scalar in this point, it diverges. So in principle cannot be eliminated just with a change of coordinates. Always we have also we also understand that we have always one single positive zero of the lapse function. So the one single horizon here, the singularity is here, the horizon is here, and in general it is possible to show that R0 is always smaller than RH for any mass, for any positive mass. So we do not have a naked singularity in full accordance with the cosmic censorship conjecture of Roger Penrose. Oh, well, this is just a diagram to show that actually the root of the previous cubic equation is just a single one. You have just one single positive root of that equation. So one single singularity for R positive. It is interesting to study the behavior of RH and R0 for large or for small masses. The horizon for large masses recover you can recover the standard Schwarzschild horizon here. For vanishing masses, the horizon goes to evaluate essentially a Planck length value, which from the physical point of view is also reasonable, since any length below the Planck length is probably physically meaningless. The radial coordinate of the singularity for vanishing masses is given by a formula like this. So it's still going to the in the limit of m equals 0, going to the Planck length. And the behavior of the radial coordinate of the singularity for large masses is perhaps the most interesting thing, at least for the scope of this talk, because it scales with the cubic root of the mass plus corrections. Just a small note, once again, we see immediately that in both cases, for large M or small m, you always have R0 smaller than RH, so the singularity results always protected by the horizon. Oh, here I have I plot in this slide I plotted the mass functions for the horizon. And for the mass function for the horizon, which is the red line here, which is smoothly approaching the green line. The green line is the mass function of the Schwarzschild metric, essentially. And then here you have the mass function for the singularity, the R0. And you see once again that for any positive mass, the radial coordinate of the singularity is smaller than the radial coordinate of the horizon. Why is it interesting, this scaling? We see that this central hard singularity is located at this coordinate, strictly positive. The finite size of this coordinate is clearly of quantum origin. Here there is h bar. If you push h bar to 0, so you take a kind of classical limit, then R0 goes back to 0, as in Schwarzschild. So the size is due to quantum, so to say. And in this framework, we can consider that if we consider a collapsing mass, M, then we can imagine that the mass is completely concentrated into the central hard sphere of radius R0. And we can compute the Euclidean volume of this object, just of this sphere. And therefore we can compute the density of this black core, so to say, of this black hole. And this density results to be finite and equal, essentially equal, apart from a couple of factors here, to the Planckian density. So the 1 Planck mass per Planck volume. So this metric describes a black hole which has a central hard kernel of finite size with a density of the order of the Planckian density. So the matter seems not to be completely reduced to a geometrical point, as in the classical Schwarzschild collapse, but on the contrary, it is distributed in a finite volume. And actually, these are exactly the characteristics of the so-called Planck stars proposed by Rovelli about 10 years ago on the ground of general qualitative considerations. Essentially, they were thinking that the finite size of the central core, being of pure quantum origin is presumably due to the action of the Heisenberg uncertainty relation principle, which prevents matter to be arbitrarily concentrated into a geometrical point of size 0. Moreover, there are also papers considering the possibility that this central kernel can, in principle, keep trace of the information swallowed by the black hole, and this perhaps could be a possible way out from the information paradox. I would like to also to make to dedicate a slide to a comparison with a previous model for the Planck stars, originally considered by, as I said, by Rovelli and collaborators. They proposed a kind of educated guess to describe a Planck star through the use of Hayward metric, which has this lapse here. And actually, there were no compelling argument apart from the fact that the Hayward metric is an example of a singularity-free metric. But actually, this metric has or presents two problems. If you expand the metric in terms of 1 over r, you do not get the term 1 over r cubed in the larger R expansion, in order to match the quantum correction to the Schwarzschild metric. So you cannot match the calculation of Donahue, so to say, if you use this Hayward metric. And a second possible problem of this expression is the fact that for large mass it develops two horizons. The outer horizon is a nice horizon. It goes smoothly to the Schwarzschild one without particular problems. The inner horizon, it goes to a fixed value, to a fixed value L, which usually, by the way, is assumed to be the order of the Planck length. So even assuming R minus as the size of the hard kernel of the Planck star, certainly such hard kernel does not increase with size with an increasing M, as on the contrary, R0 does. We have seen here that R0 grows like the cube of the cubic root of the mass. By the way, these two odds of the Hayward metric have been cured by people working on this topic using this approach. By well, essentially, they were cured by hand, modifying the lapse of the Hayward metric, introducing a by hand constructed lapse function, and they were able to recover the 1 over r cube terms. But in any case, you see that the function that you get is much more complicated than the usual the lapse suggested by the scale dependent gravity approach. Well, I think I can go to my conclusions. Perhaps it's too early, I don't know, but anyway, I will take questions later. So we have considered a scale-dependent gravity approach that suggests a general metric describing a quantum effect containing h bar. The matching between this scale-dependent gravity metric with the Donahue quantum correction suggests to the Schwarzschild metric suggests a possible negative omega parameter. And this negative omega parameter implies a geometry which gives the prediction of a finite size singularity at the core of the black hole. So the radial coordinate of this singularity is strictly positive. The size of this black core describes exactly a particular characteristic of the Planck stars, which were introduced, as I said, years ago by Rovelli, using semi-qualitative arguments, meaning that essentially they were invoking Heisenberg principle in order to avoid an infinite concentration of mass at the center of a black hole. And here, using this kind of metric, on the contrary, in our context, these consequences, they appear as a pretty natural consequence of this omega tilde negative. These objects, they also have a potentially rich phenomenology. In particular, you can have black hole evaporation with a final explosion occurring at scales much bigger than the Planck scale. Somehow they can also be associated with short gamma ray bursts. And perhaps also with some fast radio burst of extragalactic origin with wavelengths close to the expected size of the exploding hole. And I think I will finish here my presentation. Thank you very much for your attention.
Really, I have a question concerning the second part. One of your correction is a correction which was produced for very, very small momentum transfer, whereas SVG is very high momentum transfer. So I don't understand how you can identify these two things.
So essentially we match at large R. At large R, you require the matching between the between the coefficient computed by Donahue and the coefficient that you get in the scale-dependent approach. And from these, you see that this omega tilde should be negative.
Yeah, but I really doubt that SDG is given by this type of formula, because in asymptotic safety, this parameter omega is valid for a very large momentum transfer. So I don't think that this formula is applicable in the low energy. How do you know that this formula is valid at small power? Sorry, at very large power. So this
I just used this expression here for J of K, or if you want in terms of R, G of R, these. If you go to large R, you recover essentially G0. And if you have an omega if you have an omega positive, is not a problem. As I say, that you are in the framework of asymptotically safe gravity, so there are no singularities, everything is nice and whatever. In case you consider omega negative, then you develop a zero here, and you have a divergence of the coupling constant.
I wonder why it's legitimate to use this expression for G
for computation of attraction of two dots. Why? I understand that you can take this GK, make Fourier transform or whatever, but why this describes incorrectly the attraction between
two bodies, you mean?
It's very often being open.
Yeah, okay, I think I understand your point, but maybe we just we demanded the matching of the two coefficients at low energy, so to say. And then okay, maybe okay. Your point is, how do you know that the matching at low energies is true also at high energies? Yes, probably. If I rephrase
It's
your
also
question.
related, but you see, part of your computation is kind of gauging variance. So you take the GR, then you take two bodies, then you compute the energy between them. So there, everything is well defined, and you can completely extract this first corrections. But this asymptotic safety expression, I mean, it's summing up some stuff, and then this is some stuff for G. And there is a long way to relate that to two bodies.
I'm aware of this in the sense that there was also a small sentence. Let me see if I even well here there was a kind of caveat, meaning that in particular that in the last years the two communities of asymptotic safe gravity community and Donahue community, so to say, they consider possibility that actually this comparison cannot be made because probably they are summing different classes of the final diagrams or different. We got this idea of a direct comparison from the original paper of Reuter and Bonan of 2000. It is true. I agree with your point that in the last years, the communities, they debated a lot if this comparison is actually doable or not. Not doable, possible, so to say.
Thank you.
Professor, I have a question. For example, for Schwarz black holes, the singularity of Schwarz, for example, TR, the singularity is inside the even horizons, and in your series black stars, is the radius is also inside the even horizon.
Yeah.
Oh, then I have a question. Because both of them they are inside the even horizons, so is that a way to distinguish that two objects in the observations?
If there is a way to distinguish.
Yes. I say that is that a way to distinguish that two objects? The one object is perceived by the GI and the other object is perceived by your series. How can we to distinguish them in the observation? Because all of them are inside the even horizon.
From the observational point of view.
Yeah.
Well, that's a good question. Actually, quite recently, I saw a paper that they were trying exactly to answer to your question, seeing if putting a point mass orbiting one of these objects can be from the orbit you can distinguish if you have a black core of finite size or just a point, so to say. Well, of course, if you take, let me go to the metric. Yes, if you go far away, obviously our Planck star it behaves exactly like a swashing black hole. So you see some difference in the for example, in the orbits of objects around these collapsed object, close by to the horizon, most probably, just because you have this situation in which the singularity is not at the center, but is a so to say, finite size radial coordinate.
Okay, thank you. And another question. I remember that the series modified Newtonian analysis. This theory is used to explain the galaxy location first to display the dark matter exploration. Can your series also explain the dark matter such as the galaxy?
Maybe we can try to check if a lapse like that can give some, for sure, will give some correction to the standard Newtonian dynamics. That's for sure. I'm not sure if that correction will match the observational constraints of due to dark matter. So it's a problem to be investigated, so to say.
Oh, okay.
I haven't investigated this kind of stuff.
I just wanted to briefly follow up on what you were asking, maybe try to clarify a bit from my perspective, because I think I'm included in the people who doubt this comparison.
Yeah, okay.
So I think the first point to make here is that this scale identification is an approximation, which is at best qualitative, but I think it's not quantitative.
You mean the K over function? Yeah. That's I agree absolutely.
It's
Yes.
just not unique because you have a choice. And second of all, it's very hard to combine it with differomorphism and variance. So I would be very careful in taking too much on that. The second point is that you only have Newton's coupling, of course, and of course, if you have more operators and more couplings, the running is very simple formula gets modified. For the G of K, right? So you don't have a very simple rational function. Maybe the last point for this comparison, I think I agree with what you were saying. It's just two different things that you're comparing. One is whatever is in the metric, and two leading order it seems to match. It's just like that. But then if you want to make a comparison to the non-integral, you have to compute really the scattering amplitude with the physical running of K running, as Roberto explained this morning. And then, at least I think, it must come out like EFT computation, because EFT is a strict subset of this non-perturbative universal. Other questions or comments? A question. Is there any reason why the quantum effective action would just the Einstein observer and the cosmological constant? Purely the effective action of gamma.
Different kind. You mean?
Because you're assuming
we are assuming that action, yes, from as a starting point of our model, so to say.
So then you're assuming that not just for the low energy limit, but all the way to infinite energy.
Essentially, we start from there, and then we arrive to this expression of G of K, and then.
So you're applying that also the central part of black hole.
Well, in principle, yes, but probably.
Your computation.
You mean this computation? Yes.
You're assuming just Einstein Hilbert plus a cosmological constant all the way up to the center of the black hole. The effective action.
Well, we started from that effective action because starting from there, you get a correction of this kind of the G of K, and then from essentially you forget about the action and you go you do the calculation using your G of K, this G of K. So
is there any reason why this GOK should hold also if the effective action is not just Einstein people because it was modular constant?
well, I think, of course, if you question, you are asking if you can start from a different.
No, I'm asking. So the quantum effective action is something that you compute from some theory of quantum gravity. So asymptotic safety that you're using, is there any reason why the quantum
Why they use that and why they stop at that action? You mean this?
Yeah, if there is any reason to stop just at the Einstein people.
At the moment, I don't know this. What they have.
From a very simple perspective, there's a missing piece in the description, which is matter, if you want to form like quality matter. Have you ever considered the possibility to add that contribution? I know it's probably not that simple.
Not for the moment. Not for the moment. No. We are working on a theory of collapse using this kind of metrics, and
so there you are.
The next
work in progress.
the next point, the next episode.
Let's thank the speaker again.
Put all these three. And then so it's actually it's from close to this. Everything.
Oh, maybe.
Yeah, that's this is 1%.
Okay, so next speaker is Kim Grant from the Practical Physics Division, IHDP, and she's going to talk about non-quite black holes and gravitational wave echoes.
Thank you. So thanks for the invitation. So today I'm going to talk about non-quite black hole and the gravitational wave echoes. And this is based on a series of work that I've been working on, Bob, in about 5 years ago, and also with my students and postdoc in recent years. Okay, so it's basically two parts. So in the first part, I will first motivate why shall we consider not quite black hole, and then I will talk about a theoretical candidate for not quite black hole. And the second part is about the gravitational wave echo. It's basically a smoking gun signal for the not quite black holes. And finally, the summary. So we'll start with the observation. So as you know, so far, all observations identified with a black hole actually show a very nice agreement with GR prediction in a wide range of mass, including the recent observation from gravitational wave window for stellar mass compact binary coalescence, and also the first image for very supermassive compact object in the center of galaxy. So this is actually a huge success, right? Because we have verified that the theory is actually applicable in such a wide range of mass scales. However, we always want to know more. The question we can ask is that are this astrophysical black hole really what GR predicts? So here I would like to quote what has been said by the chair of the 2020 Nobel Committee for Physics. So, of course, all these observations show the great, the nice agreement for GR prediction However, this exotic object still pose many questions, including the theoretical question about its interior, but also about the observational question that how can we test our theory of gravity in this very extreme condition in the immediate vicinity of a black hole. So in today's talk, I'd like to talk about one possible answer to this question, that maybe what we have observed in the sky are not real black hole predicted by GR. They are actually horizonless ultra-compact object, which looks very similar to black hole when you observe from outside. But in the end, they could actually be horizonless. So what's the motivation to consider this type of things? So the theoretical motivation is actually quite straightforward. We know that the black hole thermodynamics and also the information loss problem are all closely related to the existence of horizon. So if there are no horizon, of course, there are no this type of problem. So if we can, and also we know that GR is not the final theory for gravity. If we consider quantum effect, then maybe there's a possibility that there are strong deviation around horizon caused due to quantum effect. And in the most extreme case, this correction could just make this object to be horizonless. This is interesting that this kind of possibility could have connection to quantum gravity effect that this conference care about. So here are some example of horizonless objects in literature. So one possibility is that you keep GR the same, right? And then you realize such kind of object by consider exotic matter. So one famous example is gravel star. Well, they think that black hole is actually a black hole mimicker is actually a ball of vacuum energy. However, in this situation, to reach this very huge companions, they need very strange equational state for the matter in between this for the matter in the surface. Another maybe more natural example is the forcible proposal in string theory. So in that case, they find that under certain ideal situation, they can find configuration from string theory which does not have horizon and which can give black hole-like spacetime in the classical limits outside of the gravitational radius. However, this proposal doesn't really apply to real black hole in our world, and also it's not very concrete. And from the observational side of view, we can consider a very generic classification of compact object by using this companions parameter. So it's defined by this difference from the potential surface radius of this object R0 and the gravitational gravitational radius. So when we consider this, it's important to think about the important length scale from observational point of view. So usually outside the gravitational radius, the most important scale is actually this three. So first is the inner stable circular orbit. This is the stable orbit for massive particle, and this is crucial for the accretion physics. If the surface can go even deeper, then you will touch the photon sphere. This is the orbit for the unstable photon orbit. If an object has the same photon sphere as a black hole, then they would have very similar black hole shadow, black hole image, and also in the gravitational observation in the prompt ring-down stage. However, if you go to very close to horizon regime, this near horizon regime is actually very difficult to probe, mainly due to the very large redshift. So basically, if you consider electromagnetic observation in this regime, due to the very short wavelength of electromagnetism of electromagnetic wave, then usually the photon emitted in this region would suffer from the trapping effect, which means that it actually can only escape this region along the direction very close to the radial direction. So that this actually the region which can really would be more thoroughly probed by gravitational wave observation, which is also what I'm going to talk about in the second part of the talk. In this talk, I basically want to answer two questions. So first is a theoretical question that are there very concrete theoretical model which can predict very compact object with this companion parameter approaching zero in a natural way without any fine tuning. And then the second part is that suppose we do have, suppose it's possible that black hole are really this type of object, then how can we identify this possibility through gravitational observation, considering that actually theoretically we still cannot have very good prediction to this type of signal. So let's start from the first part. So this example I'm going to talk about is the horizon is 2-2 hole in quadratic gravity. So in one word, the feature of this object is that it has the exterior very similar to black hole, right outside the gravitational radius, and then it has a very narrow transition region just around gravitational radius, and inside the correction, the deviation from GR take over, and it gives rise to a very noble high curvature interior. This solution is actually found in quadratic gravity, which you have been heard about during the morning's talk. Besides this theory, what we need is only an ordinary compact matter source, and then we can find this solution numerically, and it's provide a concrete example for this kind of object. And what we find is that this object, its mass range, it have a minimum mass determined by the coefficient in this Lagrangian, but its mass could be arbitrarily heavy. So this gives the potential that it could explain all our current observation for astrophysical black hole. And another interesting point is that it has a very high curvature interior, and this high curvature interior can actually give rise to interesting connection to black hole thermodynamics.
Sorry, I have a question. What's the meaning of the 2-2?
What's the meaning of 2-2? Okay, so this name actually comes from the behavior of this two metric function around zero. So basically, when we take this coordinate system, then this solution around zero, both a and b function, it goes like R squared. So this is why we call this name. Yeah. Okay, so for quadratic gravity, you have already heard in the morning that it's actually a candidate for quantum gravity in the sense that it's perturbatively renormalizable and asymptotically free in the UV. Of course, it has a ghost problem, but I think we have a lot of experts here trying to tackle this problem by considering quantum correction in different ways. So I will not talk about this in detail. So here, for the solution of 2-2 hole, what the theory we're taking is actually a classical approximation to this theory. So basically, it has Einstein term, which model that which model the GR, and it also have quadratic curvature term to approximate the UV theory at high energy. And here, alpha beta are two-dimensionless coupling. If they are order 1, then this is a strong coupling regime. Well, we only have one scale in the theory, and if they are much larger than 1, and then this gives rise to the softened gravity that Alberto talked about this morning, that they will introduce additional lower scales. It's worth to mention that in this language, here we are using this action is actually in contrast to the standard view in the effective theory, because in the Euro view of effective theory, they would have even higher order expansion. And in that case, this action can only be used to study study small curvature regime. But here, you should remember that this action is actually approximation of the quadratic gravity, so it can be used to describe a solution with both small and large curvature. So this is the important point. Okay, so a bit more detail about the feature of this tutu hole. So the minimum mass of this tutu hole is actually determined by the Compton scale. This Compton scale associated with the ghost. And if we so basically if this lambda 2 is Planck scale, then this minimum mass is the Planck mass. So as found by Bob, actually this narrow region I just mentioned, it actually will become it will decrease very quickly with large M in this power. And also for this noble integral, we notice that due to this dominance of quadratic curvature term, it exhibits a very different scaling behavior, which means that the tutu hole with different physical mass, this integral would be related in a way very different from general what GR predict. And what's also interesting is that this hole could be sourced by different type of matter like photon gas or Fermi gas. However, we find that actually the property of the hole in the end is insensitive to the matter source. It's mainly dominated by this quadratic curvature term. And as a result, it's give rise to very interesting thermodynamics. So if we consider photon gas as a matter source of the hole, then you will see that the temperature at infinity for this gas would be just proportional to the Hawking temperature up to small order 1 correction up to order 1 constant. And its entropy is also proportional to the black hole entropy. So this provides an example that how this holography actually could, holography type of behavior can actually emerge from a high curvature effect. And we have also considered more general thermodynamics discussions on this type of background. And we noticed that actually the special feature of this object can be captured by something called the thermodynamic volume. And this strange behavior, say like related to thermodynamics, are actually all related to a very huge thermodynamic volume for this object in the interior. And this actually leads to when you consider when you compare the internal energy and the physical mass for the object, then you will see that actually a lot of energy, physical mass of this object come from gravity. And putting it this way, we can also recover the black hole like first law of thermodynamics for both photon gas or cold Fermi gas. And another interesting prediction of this for this object is that what I just mentioned apply to a typical tutu hole with its mass much larger than the minimum mass. So in that case, you can imagine that if back to early universe, this tutu hole, just like primordial black hole, can be formed by primordial density perturbation, and then it will radiate like a black hole with higher and higher temperature. However, in this paper, we noticed that its thermodynamic behavior actually would become very different when its mass approaches the minimum mass. In the sense that its temperature will actually drop. So will drop. So this means that when it radiates into this regime, it actually will leave a remnant, which can leave a remnant with reduced power. So this remnant can actually naturally become a candidate for dark matter. And the fundamental property of this dark matter are all determined by this minimum mass of this theory. So it's actually a very predictive and economical model. So if we consider potential observation for this type of tutu remnant as dark matter, then if its mass is sufficiently large, of course, it will be probed in a way similar to a primordial black hole. However, if we consider very small remnants, then there's a very interesting phenomenon associated with a potential merger of these remnants. This is again related to the thermodynamic behavior I'm talking about. Although each remnant is very cold, after they merge and reach thermal equilibrium, they could reach very high temperature, just according to according to the plot I just showed. So this very high temperature object, of course, then will radiate energy and radiate a bunch of high energy particles to release this additional energy, and this would produce additional photon and neutrino flux at least, and maybe something else. So we have trying to use the current observation of this photon in the for the photon and neutrino flux to impose constraint for this type of dark matter. So this shows that actually this theoretical prediction indeed has very immediate interesting phenomenological implication. And another application is related to this idea called the scalarization. So we know that the black hole, there are no Hell theorem for black hole, and if you wanted to grow scalar Hell for black hole, then you have to add something else. So in the literature, usually, like people have to modify the theory, like they have to consider. So for instance, they can consider scalar tensor theory in some form, so that they are able to have a scalar profile for black hole, but not like in the wave gravity regime. And this is interesting because currently we're able to probe this strong gravity regime. But the other more say like a more ordinary case is that we can consider for the neutron star, just simply due to the finite energy or temperature effect. If there's some scalar like axion is coupled to neutron star, then this effect could grow scalar Hell for neutron star, and it also have interesting observational implication. But now, because we are suggesting that maybe all the astrophysical black hole are 2-2 hole. So in this sense, this high temperature or density gas inside 2-2 hole may provide a different, a new way to generating non-trivial scalar profile for this object. So this is what we have been studying recently. So the final result is that so we can indeed produce scalar profile with the scalar charge to mass ratio around order 1 in certain parameter space. And this is mainly attributed to the very high or very extreme environment inside, which cannot be realized in other places, right? So in this sense, it's provide just a view, just provide a way for us to probe potential beyond standard model new physics at high energy scale. And if this and we also have very different prediction for this ratio compared to other theory. So in this sense, this different prediction could be probed by gravitational observation, say like through the identification of coalescence time for binary or the dephasing for the extreme mass ratio inspired. Okay, so then let me go to the second part about gravitational wave echoes. So basically, as an introduction, currently GR prediction. So currently we have the LIGO have observed about 100 event for compact binary coalescence like this, and the GR prediction for this 3 stage, the inspire, merger, and ring down has been confirmed. However, as mentioned or highlighted by this paper, just right after the first event detection, is that this observation is actually not sufficient to directly identify what's going on in that near horizon regime. Because as you can imagine, if there's something going on very near horizon, then due to the light redshift, those correction would the signal generated by those correction should take some time to come out to be observed. So actually in a later paper, they propose that they propose that if the horizon, if the boundary condition at horizon has been modified, for instance, if you have horizonless object, then a smoking gun signal for this correction is actually the so-called gravitational wave echoes. And this also motivates a lot of research trying to trying to have a deep search of the long duration post-merger data. So more specifically, the idea of gravitational wave echo is very simple. So the propagation of gravitational wave on a curved background can be simplified in this way. So here the essential ingredient is this effective potential here. So for black hole, this top panel plot is effective potential. So it's basically feature a potential barrier around the photon sphere. And it's exactly this barrier produce the photon produce the inertial ring-down signal that LIGO currently have seen. So now if we have some horizonless object which have similar barrier here, but some large correction like more close to the horizon, then if there are some perturbation propagates or generated inside this regime, then you can imagine just like what ICO is like, then this the existence of this additional reflective boundary would produce a train of additional pulses after the initial black hole-like signal. Why is this related to quantum gravity? Because if you are thinking about some quantum gravity correction at a radius at about a Planck length away from the horizon, then due to this, because this redshift is proportional to the logarithmic of these two different length scale, then you can calculate that a Planck scale length scale actually just give you order 100 time delay compared to the typical time scale of black hole ring down. So this means that our current observation is actually sufficient and have long enough data to probe this additional pulse potentially related to quantum gravity effect. So the question that how do we search for this type of thing? So in GR, people do they search? The most traditional method is that you create some template based on the theoretical prediction for the waveform, and then you are using this matrix filtering method to dig deep into the noise and to find out a very small signal. However, for ICOs, the main problem for this is that the theoretical prediction for the waveform is actually quite uncertain. So for instance, the early attempt start from very toy, simple toy model, and later they consider like more realistic case by using black hole perturbation theory. However, there's still theoretical problem, even in that type of simple model. And actually recently there are actually more realistic numerical simulation for a boson star, which is also a candidate for compact object. And this is what they find for the ICO waveform. So the thing that this waveform is actually very different than what I showed before, which is calculated in a very simple case. So the message I want to tell here is that to find this signal, actually the template-based method probably is not enough due to this large theoretical uncertainty. And actually, we probably need a quite model-independent method. So let's consider a more concrete case. So if now we consider a truncated curved black hole as a toy model for this ultra-compact object, then the ICO waveform can be generally constructed in this way. So basically this it can be factorized into these two factors. So one factor is related to the effective reflection for the inner boundary, and the other one is related to it's encode the inertial condition or the source dependence. So as you can imagine, both parts are actually quite uncertain. So the question is that how we do the search considering this very unclear theoretical prediction. And here what I showed is a screenshot from the white paper of LVK collaboration. So as you can see, as one of their goal is to search for icons in both template-based and also model-independent way. So this model-independent search actually, I'm trying to convince you that this is actually what we should more follow in the future. And this is exactly what LIGO has already considered in their more recent papers. They are using such a quasi-periodic signal, quasi-periodic signal with a small number of pulse as a model-independent description of icons, and to do the search, and they didn't find any evidence, clear evidence for icons. However, the problem is that this picture is not actually the whole story for icons, because as you can imagine, if the interior reflection is awake, then it is awake, then this pulse is small, so this type of model could be efficient. However, if the interior reflection is strong, then you may have like a large number of pulse. So it's very difficult to describe these things in a very economic way. So in this case, then we notice that actually a more useful way to understand icon is to do Fourier transform to the frequency space. And then you will see that then you will find that this icon is actually basically a superposition of a large number of long-lived and quasi-periodic quasi-normal mode of this ultra-compact object. So this shows you some examples. So here we take different benchmark models by considering a different model for this interior reflection and this inertial condition dependence. So this spikes you can see here just correspond to this quasi-normal mode of the object. So basically, these are our search targets. So actually, we are trying to develop some method to look for this long-lived quasi-normal modes, actually already in many years ago. And the initial step is suggest to use some periodic and very uniform waveform to capture what I just showed you, because in this case, you would have very small number of parameters to do the search. And later, Bob also have done some search on the real LIGO data by using the frequentist method, and also reported the interesting tentative evidence for the icon. So because of this, then we are also thinking that maybe we should develop some Bayesian search method for this type of signal, because this is what LIGO collaboration currently use more. So the key point here that for Bayesian analysis, we have to identify the appropriate likelihood used for your signal. So this is what we use basically by integrating out all the phase information to do the search. However, after we're doing this, we realize that probably if we just throw away all the phase information, that's too much. We want to see, is there anything in the phase that can be used, but without adding too much other arbitrary things. And then we notice that the phase for the quasi-normal modes could be separated in this form. And actually, there was one part inside this phase is directly related to the amplitude that we are looking for. So, so if we are able to incorporate this phase information in our search, then this will help to increase the efficiency of the search method. And we also notice that the additional contribution actually in the narrow mode limit is actually roughly a constant. So the improvement is then very simple. We just need to do the coherent combination of different frequency beams to keep the relative phase information and just marginalize over the overall phase. So in this way, we can get a new likelihood which has a better sensitivity to this quasi-normal mode. So this is our one more recent work. So here I just want to show you our search results. So when you develop a search method, you have to verify that this method works. So what you do is that you can consider a few benchmarks for your potential signal, and then you inject this signal into a large number of Gaussian noise, and then you do the search. So here are our search results. We consider 4 benchmark, and as you can see here, you probably don't need to know the detail, but you can see that they have very different shape, and our algorithm, like in this different corner plot, can capture, can find out the signal, which can be seen by this distribution of Bayes factor, and it can also give very good inference for the parameter, for the important parameter of this signal. And these are some additional search results. So basically just say that, okay, we can do this work efficiently. So finally, we need to do this in the real LIGO data. So what we do is that we need to have a good understanding about the background, because the data is not exactly Gaussian. So the non-Gaussian part that really contributes to this search is this instrumental line, which is also very narrow spike in the data. So here, what I want to show that we can do something called notching, so basically to get rid of this lies in proper way, so that this background distribution could behave like the Gaussian noise, so that you can do this search on the real data. So we also need to inject a potential signal in the data to show that these things work. But unfortunately, in our previous paper, we do this search with our old likelihood for these 2 events, and we didn't see the clear evidence, so didn't basically confirm the previous tentative evidence. But recently, we're also keep working on doing this search, like more with this new method on more events, and hopefully, we hope that we can get some new things. So in summary, so I want to conclude with this quote from a SNOMES paper. So basically, with more and more data from both gravitational wave and the multi-messenger, actually the black hole physics become more and more like an observational science. So I think this is really a good time for people working in theory and observation to work together to finally do the real physics. Here I introduce one concrete example to show that the Planck scale physics can indeed manifest naturally just right outside the gravitational radius for very large objects. And this could have interesting theoretical and phenomenological implication. Then I talk to you about this smoking gun signal called echoes, which could be a very general way to distinguish not quite black hole and black hole. So yeah, that's it. Thank you.
So I have some questions. The voice is that any completions for the formation of the two holes? I remember the next is it can be the candidates of after it's true.
Yeah, it can be the remnant.
Yes.
The remnant.
The fourth question is that any condition for the formulation of that two hole like a black hole at the massive upper bound?
You ask whether there's upper bound for the two hole mass or
yes, like a black hole condition to form a black hole or the condition to form a two hole. Is that any condition?
Well, so here what we did that we just find say like a static and spherically symmetric solution. So we haven't studied the formation problem in this theory, because as you can imagine, due to the ghost problem, the formation is hard. So we haven't studied that, but for the gas, I think black hole will form say like above 3 solar mass, something like this. So I think because we're saying that this theory is very similar to black hole in the exterior, right, in the low curvature regime. So in this sense, I think that threshold may also apply to the hole. So basically, we don't expect other things to happen, like in low curvature regime or in low density regime. Yeah.
Okay, the reason I to ask this question is because I want to know if that condition can be satisfied at the early universe. You have asked you have answered my question. Thank you.
So sorry?
No, the second is now a question. The second I explain why I asked for those questions. Because I want to know if that condition can be satisfied in the early universe.
Right. I mean, in early universe, just like primordial black hole, right? You can form whatever mass you want. So that's, I mean, that, yeah, I think in that sense, I think there's no constraint.
Okay.
Questions and comments?
So this is the virtual star, like instead of black hole.
So what I'm talking about is not a gravitar star. So if you're talking about 2-2 hole, it's a different type of candidate for ultra compact Huranic object.
Yeah,
so
it's horizon.
Yes, Huranic. So in this sense, it's a bit similar to star, right? But it's not a star in the sense that it's actually have a very high curvature interior, and actually it has a singularity at the origin. So in that sense, it's not a star. So for star, you would have a regular space-time in the inside. And also for a regular star, usually it's very hard to make it as compact as a black hole.
And if this is horizon, does this mean that the matter can leak out of the
Yeah. Right, so things can come out, but as I mentioned at the very beginning, so the reason that it's very hard to observe this type of thing, say like from electromagnetic window, right? Like by photons, is because that they looks very similar. I mean, they deviate from black hole only in the very in high redshift regime. So in those regime, actually the particle can easily be trapped inside, so that the final flux of this object will be just extremely suppressed. So in that sense, the luminosity of this object will be very small. Although in principle, yes, without horizon, things can go out. So in this sense, there are no information paradox, right? Because things can go out. Yeah.
Any questions or comments? Actually, so is the action computing solution of this that you have, it's 2-2 holes, is the action large in units of the Planck H bar?
I think you mean inside, right? I mean, it's a function. I mean, this solution is function of radius.
No, the action. So the action is not a function, right?
You mean action
Action
after the integration?
Well, divided by space volume, so.
Well, I'm not sure I have calculated that. Yeah. Yeah, because I think we.
I mean, I'm looking for a justification of using the classical limit in presence of
classical limit.
This extended. So because you saw the equations of motion in the presence of some sources.
Yes.
And you use the classical limit.
Right.
You use the classical equations of motion. So I was looking for a justification.
You mean why I can do this? So you think only when the action is large, then?
Well, if this is not the case, how you should take into account the quantum effective action, which is a different function.
Right. I guess also in say like your proposal, right? Then there's no quantum fraction. So
the
that
condition is just the same as the normal theories. The action should be large in units.
Okay.
H bar.
I see. Yeah. Indeed, we are just using the classical one. Yeah.
Okay, let's end this.
Okay, thank you.
On the string. On the string. So we have a three. At the bottom. From the bottom, it's like. Oh my God. So this one.
Okay, first of all, and speaker is Benjamin from Beijing University of Technology, and he's going to talk about access and additional motivation with rotating compound objects.
Okay. First of all, I would say thank you so much for the organizers for inviting me to give this talk today. And obviously, you can hear I catch a cold and hardly speak loudly. So if you have any questions and if you cannot hear clearly, just feel free to ask me. So the topic of my talk is about actual gravitational predictions of slowly rotating objects, which is based on our recent works. And in this topic, I will focus on these several topics. First of all, I will introduce why we want to start with the black hole prediction series. And secondly, as is compared to Yunjin's talk, she paid more attention on the applications. Well, in my case, I will pay more attention about the techniques that we use to do the predictions based on different backgrounds. So I will take some time to introduce the standard method that we use to do the predictions of static black holes and spinning black holes. And furthermore, I will introduce and solve the problem so far of the prediction of the spinning black holes. And then I will move on my recent work, which I will focus much on the predictions of the slowly rotating black hole, and I'll be using the semi-analytical techniques to do this. And then I will give some applications on my results, and the last I will give summary and discussion. So there are several reasons for us to start with black hole prediction series. For example, analyzing the stability, especially the case when a black hole experiences super radiance, and the stability becomes increasingly crucial. And by analyzing the quasi-normal modes, one can determine the stability of a black hole experience disturbance. And understand that this phenomena is of great importance for us to understand the black hole dynamics and its evolution in the universe. And secondly, as we all know that the Noether theorem guarantees that the stationary solution in GR must be axisymmetric and described by curve metric. However, we all know that this is not the case in other modified theory, which solution deviate primarily from GR counterparts. So I think studying the black hole prediction theory is in some sense will help us to detect the deviations from curve black hole, because as we all know that the near future gravitational detection will prove the strong gravity regime. And in this regime, in principle, we can detect the deviation from the curve metric. And secondly, it was proved that there are some connections between the quasi-normal modes and the Hawking radiation. And I think all of us know that the quasi-normal modes describe the dissipative properties of a black hole, and the Hawking temperature reflects the thermal radiation properties of black hole. And it was discovered that the imaginary part of the quasi-normal modes is proportional to the Hawking temperature. So it has some connection with the Hawking radiation. And furthermore, we can also use the prediction theory to study the gravitational wave. Let's see this picture, which describes that the last stage of the Pleasance or binary black hole, corresponds to the process that the random wave oscillation tends towards stability. And in this stage, we can use the perturbation theory to study it. And its random wave is characterized just by the polynomial modes. And I should say more generally, if we consider two body objects, and but they are at a distance, and then the gravity is relatively weak, and then in this case we can use post-Newtonian approximation. And if they approach each other and enter the region, which is a strong gravity regime, and then they need to use the numerical relativity. However, there is a special case, which is a significant small mass object orbits around another much larger mass object known as the extreme mass ratio in spiral. And in this case, actually we can use the perturbation theory to study the whole process. So there are several reasons for us to study the black hole perturbation theory. And also there are also another applications in ABS, CFT, and etc. And I will not talk about much on this. And next, I will just take some time to introduce the standard method of the perturbations of a static black hole. Here, what we show here is a spherical symmetric spacetime and its perturbation represents by h mu. And due to the spherical symmetry of the spacetime, what we can do is split the index into two parts. The first part is TR, and another part is sigma phi. And then what we can do is we could decompose these perturbations h mu into scalar type, vector type, and tensor type, based on the transformation law of the isotherm group. So here we can see, for example, x mu is a rounded symmetric tensor, and its components x, a, b is obviously a scalar type because there are no index a, b is just from TR, so there are no index from sigma phi, and obviously x, a, I is a vector type perturbation. But furthermore, we can also decompose this kind of perturbation into the divergence part and the transverse part. And similarly, we can also decompose Hij into the trace part, divergence part, and the traceless divergence part. So in this case, what we can get is that we can decompose the perturbations into later perturbations, which have no index from sigma phi, and vector type perturbations which have only one index from sigma phi, and tensor type perturbations which have two indexes from sigma phi. And because we are working in the fourth dimension, we can see that the traceless transverse h mu hat has 0 degree of freedom. And furthermore, we can expand the predictions using spherical harmonics. And then we can expand the scalar perturbations using axial perturbations and axial harmonics, and the vector type perturbations using the power harmonics. And then we can get this equation 7. So just to summarize what we have discussed so far is that we can decompose the perturbation variables into scalar type perturbations, which we have 7 variables. We can also call it power electric, and we can also decompose it to the vector type perturbations, which has 3 variables. We can also call it axial of magnetic perturbations. And because of the big gauge theory of gravity, here possess the multiple symmetry. So the perturbated ion equation in the environment under this kind of gauge transformation. So we can conventionally choose the gauge cosine A cosine I hat to 0. And this stage, we can look back. So what they do, they just set this divergence term to 0. And this is the famous radiator gauge. So far, now we can classify the perturbations into into the polar tab and axial tab. And here are the basic form. And then we all know that by introducing proper-normalized variables beside we can obtain the shipping equation, which the potentials are obtained by Radiator in 1957 and already in 1970. And here are the potentials. So next problem is we try to solve the eigenvalue problem. Well, unlike the idealize the microscopic system, the black hole is intrinsically dissipated due to the existence of the event horizon. So we must impose the pure ingoing boundary conditions at the horizon and pure outgoing boundary conditions at infinity. So that this precludes the standard normal modes analysis study. So because of the system is now time symmetric and the boundary value problem is not a mission, so that we must work on quasi-normal modes, which are usually complex. And here, this part is the real part, and it has the imaginary part. And the real part usually corresponds to the oscillation's frequency, and the imaginary part usually corresponds to the batting rate of the amplitude. And it can also be shown that the eigenfunction is non-normalizable, so it cannot form a complete set. Actually, in the real world, almost every system is intrinsically dissipative. So one may reasonably assume that orthogonal modes is ubiquitous in physics. So next, then the Chandrasekhar in 1975, and he found that the isospectrality of the axial perturbation and the polar perturbations, and then he found the transformation law between these two potentials, as shown in 21. Now we are considering the structure of black hole, which is a Viking solution, which means that we can treat the different perturbations, the different field perturbations with various spins separately, so that we can write the potentials of the fields with various spins in a uniform way as in 24. And we also list the field perturbations with different spins. See this. And then let's move on to the iron black hole, which is different from the structural case. Here exists the electromagnetic on background. So there must be something different. But similarly, we can also follow the techniques that we use to decompose the metric, and we expand the electromagnetic potential as follows. Here we have 3 polar variables and 1 angular variables. The differences is for simplicity, let's see only the axial perturbations. We will find that H2 corresponds to the perturbations of gravitational field, and H1 corresponds to the perturbation of electromagnetic field, and you will find that the perturbations of these two kinds of field coupled with each other. You will see here H1, H2, here H1, H2, so they couple with each other. And what's luckily is if we introduce 2 new pair of variables, Z1 and Z2, which is a composition of the various variables in H1 and H2, what we can get is decoupled shading line coefficient, which is the narrative effects. And if the black hole that we are considered is an actual physical black hole, then we can also assume its charge is really small, which is much smaller than F. Then in some sense, we can freeze something because like look at this. If Q is set to 0 and then we can ignore this term, and what we left is only the differential equation which in terms of gravitational perturbation, and in this case, the effective potential is just the radial potential if we have Q equals 0. And similarly in this case, we neglect the dynamics of the gravitational perturbation, then we are left differential equations only in terms of H dot, which is the perturbation of the magnetic field, and in this case, the potential is just the perturbation of the electromagnetic field on the background structure. And now we move on to the spinning case. We consider our curved electron. Okay, the perturbation of curved electron we started with the Newman-Rosen formalism, and this approach works by projecting the spacetime onto the non-empty picture. Then by analyzing the geometrical relations between some components of the projected wire tensor. So comparing to the metric formulation, and we can understand this kind of method as a curvature formulation. And Tchaikovsky, he gets the perturbation equations with separated variables. Here you can see this is the angular part and this is the radial part. And what's more, let's move on to the current one. So there is nothing different. Back in the R case, where we fix the electromagnetic field. So what we can do is just to decouple the electromagnetic perturbation and the gravity perturbation. But so far, all attempts to decouple the electromagnetic and gravitational perturbation of the current spacetime have failed. This is proved by Chernarasek in 1983, and the linear perturbation equation was shown in 42. And Mark and his colleague in 2014 rewrite the equation in the metrics form. Now we can see the cosine 2 and etc. Right represents the perturbation of gravity and the perturbation of electromagnetic field respectively. So we could see, because this is a metric, we could see that this kind of two perturbations coupled to each other. And even we can set Q equals 0. Then it seems that we can get decouple the perturbations of this Q kind of we can get a couple of perturbations, but here is another I think it's an important problem because they want to separate the variables, but it's impossible because here are F, G, and the third H are derivative operators in both R and theta, and it's very hard for us to separate these variables R and theta. So let's remove what we have learned so far. So we can decompose any perturbation around the generic static background and reduce it to the one-dimensional eigenvalue problem. And using anti-formalism, we can calculate the perturbation of curved electron and reduce it to a two-dimensional eigenvalue problem. But if we want to apply the predictive approach based on anti-formalism to a generally full rotating background, we face the two issues. So first of all, the matter field always coupled to the gravity is not lead us evident separation of the variables in the perturbation equation. Secondly, usually the analytical full rotating solutions is unlikely to occur in alternating theory of gravity. So what we do is that we will focus on semi-analytical method. We focus on slowly rotating black holes. So in this case, things becomes possible. But because we are working on flow rotating approximation, so the small spin parameter can be treated as the modification of the second case. So all the techniques that we use to decompose the metric and the data choosing is still valid in this case. Similarly, we can expand the perturbations in securical harmonics. But upon the variable separation, there is some problem. We found that different multipoles coupled to each other. This work is done by Paulo in 2013. Here we gave a general metric access of slowly rotating black hole, like in 43, and the radial perturbation equation was shown in 44. And you can see this AL, PL are all represented for axon perturbation and polar perturbation. And you can see they couple together, AL, PL, and the people with a multiple index, L plus 1, L minus 1, are coupled, all coupled to each other. But we know that our system has this kind of parity under the spatial universe, so that the field equations and boundary conditions are invariant under this kind of transformation. So this leads to the eigenfrequencies must have this semantic form, which means that I should emphasize that time mass couple is A. So it means that this kind of term, which only in terms A without M, will now contribute to the eigenfrequencies. So what we get is just this term. Which we find that the axon perturbation and the polar perturbation are coupled, and different multiples index are also decoupled. So what we do, our work focus on is we know that the curve metric, the deviation from the curve metric made from the surroundings, like the accretion phase, gels, or dark matter, or even the case as mentioned by this the objects that we are studying, the stars or that are exotic compact objects. And on the other hand, of the theory, in the full analytical spinning solution in alternating theory of gravity is unlikely to obtain, but somehow the slow rotating solution is much easier to come by. So from these variations to phenomenological point of view, we just assume the solution that we have is supported by an anisotropic fluid, which means that without loss of generality, we can assume that slow rotating black hole is the solution of the effective Einstein equation. And here, d mu represents the anisotropic fluid. And then we just do the perturbations of the Einstein equation. And here, we found that there are 6 variables of the power perturbation of the stress tensor and 2 variables of the perturbations of the stress tensor. And what we do is in a feature formalism, we do the formation of the background equation, and then we can get the components of the perturbative stress tensor. Here is shown in this pattern. What we can see, and this kind of term represents the momentum flow. If we assume the fluid has no fraction, which means that Q plus H1 Ln equals 0. This represents this Q is the perturbation variables of the stress tensor, and it can be represented by the perturbations of gravity. And we can further get 3 equations For the epsilon perturbations, epsilon in 59 to 61, and from equation 61, what we can get is ULM equals minus HULM, which means that another epsilon position in the stress tensor can be represented by another gravitational position variables. So that we can see that in this case, the gravitational provisions and the stress tensor provisions decouple each other. And they are considered only a slowly rotating case. So I mean, the parameter A contributes a linear correction to the static cases, so we can assume the master variables have the following form. And then we can obtain the shading line equation and the gravitative function H1 is represented by 64. And we can get the potentials, which is the part that we are curious. So V0 is just the potential of the static case, and VA is just a small spin fraction. And here we will see that A, B, C, D. They are just the functions in the metric. So here we can see we didn't use based on any specific metric of theory. So what we have obtained so far. So we found that the metric predictions decouple from gravitational predictions for actual sector. And what we get, the effective potential is just a modified regular potential. And we didn't base on any matching or any theory. We just attribute the parameterized deviation from GR to a phenomenological stress tensor. For results are applicable when the dynamics of the material or high dimensional operators can be neglected. So to validate our results, which we get in the previous formalism 65, remember the potentials of V0 and V8, then we will give two examples. And this is the first one, the Kerr-Newman perturbations, and here are the functions in the metric. And what we do is just substitute this function 66 to the previous formalism that we get in the 65. Then what we get is the potentials shown in the 67. If we look at this, it's minus 6, and this potential is just like come back, we call it the Rn case. Yeah, this potential you see is just the Rn case, which they freeze the dynamics of the electromagnetic, which means that we can just ignore this term, and then the potential left 3m, 3m, 6m, just the potential that we use our formalism to get the same results, which validates the effectiveness of our results. And theory A is just the small spin modifications. So these results supposed to give the gravitational coordinate modes of slowly rotating and vaguely charged Kerr-Newman black hole. Another case that we have is around the iron cubic gravity, which we consider the cubic curvature term is shown in 69. And the spherical symmetric black hole up to first order decoupling constant epsilon is given by 70. And then what we do is, well, because the common parameter we are considered is relatively small, so we can substitute the zeroth order GR equation to reduce the problem to a second order differential equation, so we get the equation 72, and we get the vacuum potentials and the class matter represents for the actual and the polar potentials in this case. And what we can do next is use our formula just to give you this kind of metric function to the formula 65, and we get another potential. Here we show here. We have, but we only calculate the axial case. And what we want to do next is using this sorting method to calculate the polynomial spectrum. And here we give two plots. The horizontal axis represents the total constant, and the vertical axis represents the real part and the imaginary part to that in geometries, the ratio to that in geometries. And here there is two plots, and you will just find that the differences between these polynomial modes is 0.5%. And one epsilon is really small, and in this case, the differences in some sense can be neglected, but epsilon is larger. And then so you see the differences in more or more obvious. So in this case, we probably need other methods to validate the effectiveness of our results. Okay, so let's conclude what we have done so far. So we found that the effective of the small spin of black hole linear perturbation is just to modify the rate freedom potential. And the modified potential gives the gravitational polynomial modes one that neglects the dynamics of the vector field or higher dimensional operators. And we also hope to generalize our method to arbitrary order in the slowly rotation approximation. But the prediction equation becomes increasingly complex. So what we think we need to develop more mortality and semi-analytical method. And we also hope to build a connection between the metric perturbation based on the spherical harmonics and the curvature perturbation based on the anti-operator. Okay, here are my thoughts, and thank you for all of your attention.
Questions or comments?
Hello. So can I ask a question? So, what is the problem for generic non-static rotating case? You can't separate variable. It's only the
Let's come back to this slide. It's actually the Kernuma case. Kernuma case. The problem is that we found that the perturbation of the electromagnetic field inside that, and the gravitational field inside two are coupled each other. This is the magic that you know. And the problem is, even if we try to decouple it, we just ignore the Q. If that Q is very small, then we can get decouple the equation of the gravitational variables and the electronic gravitational perturbations and the electronic perturbation. But the problem is, what is important that we want to separate the variables R and say I. But because of the derivatives F, H, G, our derivatives in R and theta, and then especially G has some cross sections terms, so that they cannot. It's hard to separate the variables, which is the essential part.
Yeah, that's for the Newman case, but for your case, you are writing all possible deviation from GR or matter field with the scalar anti-moment tension. For your case, why you have to
content you don't know agency?
Oh, is that because we want to use, the very new thing, and we also use, talk about purpose, we are all based on the NP functionalism, and the problem is they cannot separate the variables, but they want to separate the variables. So what we do is just we choose to treat the rotation, the angular momentum of the black hole, A is very, very small. So we hope we can do the calculations, phase on background, which is approximate static value. So in this case, we want to apply all the techniques of the metric decomposition and gauge shifting, and then also the all techniques. In this case, we want to just apply all the techniques. So we want to make the problem much easier.
Yeah, for your final result about what's normal, usually you assume some form of some multiplication of GR or some method form. What is how do you choose that?
You mean that we didn't use any specific metric, right?
Yeah.
I didn't choose a specific metric. Yes, here we just give general metric assessment. A, B, C, D is arbitrary. Is arbitrary function, depends on the exact theory which is this solution is based on the full equation motion of that.
When you solve the polynomial mode, you need this the exact.
Yeah, it is a perturbation around this method.
Oh, you don't need the exact form of ABC.
Yes, but we attribute the differences from curve metric to the momentum method. So we can say literally like just put all the heritability into the right hand side and treat it as static tensor, but ignore their dynamics.
Okay.
Yeah.
Thanks.
Questions?
When you remember why you turn the cube term, not the projected term. When you give the example, you are assuming the interaction of gravity.
Oh, so
I want to give
I
the
just
second
gave the example of the cubic theory, isocubic gravity. I just gave an example. I just want to validate our results when the coupling constant the lambda is really, very small, and then the which means that in some sense we can ignore the dynamics of the higher dimensional operators. So in this case, we want to validate our results that the formalism that we gave is effective. So we just take an example. We can do other theory. If we also want to do the other theory, or we want to base on other backgrounds, maybe like dark matter as the energy momentum tensor. So you can do.
Speaker again.
Again, some problems there, okay, and you may not pay attention. Yes, and we can find here.
So
In the same direction.
I think we did different from my setup, so different. No, so okay, so what we have in mind is that also the so at least European is really right. Okay,
We start from the ideal solution. In this case, we shall variance. But we can use sorry to understand. If we want to look at the following age consideration. Or something like that. And then we show then we show this motion with this initial condition and we do the
yeah, okay, so I understand your proposal. After I understand the time dependent to run does not matter.
Well, if it doesn't matter for this. Not that I this is nothing should
So, I do not have the idea how to describe the time
Not exactly. Not really. Actually, I don't think it's not exactly. But some stuff. I don't think that's the games have some information which become this is not necessarily describe the universe, right? But answering the question of what happened with the okay, but anyway, so what you guys say that by doing in this way, if we identify that here and do that, okay. Anyway, so then this familiar system of equations. I mean, the solution is this not space and in this way, the times are all the linear equation, okay, so how are we going to be good things and how do we have like? Well, yeah, that also was confused. We get some of this. Okay, and this is the invariant. This is not yeah, so the up to one. Yeah, but this is okay. That's why yeah, okay. I think this is something you have already written in your paper. So I need to work in and then compare to this is also up to this and then after everything you have new guy and so then
windy power. Say.
and this is also
Which one?
Yeah.
Yeah.
Then so this could be understood like something like the is there. Like
Very sunshine line. Recon. It means like sunshine, like okay.对上不够容易。我们这边有两个美线上的那些参会，就麻烦你把它挂在这边挂。Oh, it's not on, so. 谢谢。然后如果您需要这个就是现场的买的话，就这个。或者有这个，这两个都是新的。It is nothing to hold. It is adequate sound is coming. Oh, okay. Yeah, it's fine. 就是说声音。Yeah, yeah. Just 很理想。I think you can just plug it in your collar. 这个。Yeah. This one. Oh, no, this one. This one is fine. 一颗它不发吧，这个的话，你只能靠近才有声音，就稍微远一点，到这儿可能它这边收到。它不要太大就行。Yeah, it is fine. Yeah, but it is a new. Yeah. 然后是那个激光laser光来看。对，是专业。
I said this you're这个谢谢呀，对。
No, I'm just finding that who is the chairman of G-Bank.
This lady. I have told her that we should use this. Otherwise, the project I cannot hear from.
Questions.
Actually, the outcome is kind of nice. As your microphone seems to capture sound from far away. Expensive one. They just avoid capturing sound from far away.
I see.
The cheaper one, they can capture all sound.
Right. That is true.
But the final effect is kind of better.
So A Z to T in X. T initial and X so T is T. You don't tell anything about T. So after that, I do not answer B equals constantly equals something that was right. So you use direct thing like okay. No, but I think no. Yeah. For me, get here is not I get
Okay, so let's start the last section of today. So the first speaker is Dr. from Institute of Science. Please talk about growing rapid
So your proposal is that okay.
First I would thank the organizer for the effort to put this nice conference. So the title of my talk is Proving Gravity by Gauge Series. So this is based on the work with my students, Li Zheyu, in the end of last year, and also some ongoing actually we finished this work in presentation with also Li Zheyu and Tu Guorui. So the topic of this talk is basically about the color command realities and double copying, which is particular what I mean here. So here is the outline of the talk. I will first give some background introduction. Then I will tell you how to the techniques about constructing color command dual numerators. And the third part is major new results of this talk. We will introduce a new strategy of doing deformation. And finally, the summary and how to. So I know the audience has a very diverse background. So I have background about doing high loop amplitude computation. So please feel free to interrupt. I will try to make it less technical. So first, after motivation, we all know that the STEM model has is a nice framework to unify the three fundamental forces. However, the third fundamental force is gravity. Is still, we don't have a perfect model to unify all of these four fundamental fields. So, and the essential question is how to define a quantum theory of gravity. Okay. And actually, Feynman was among the first to try to attack this problem. This is the preceding paper in 1963. So he tried to study the quantum theory of gravitation. At the very beginning of this the talk, we made a few very interesting remarks. I just quote what he said here. So there is a certain irrationality to any work in gravitation. Okay. And as two examples, they show this irrationality shown in the strange bodies of Professor Weber. You know what that is? Gravitational wave detector. And also there is observed creation of Professor Weber. There are black holes and wormholes. So nowadays there are also verified experiments. And he also said that I'm investing in this subject despite the real difficulty that there's no experiments. So this real difficulty we still face, I think mostly facing today. Do we have a real quantum evidence for the gravity? And of course, by studying quantum gravity, Feynman tried to do a loop computation. I just recall that even at time how to quantize the mu theory is not known yet. So just through this study, we make two very important discoveries. One is the so-called Feynman tree theory. Basically, it's how to decompose the one loop amplitudes in terms of tree amplitudes. And another is, I think it's more important, he basically framed the idea how to do path integral quantization using this nowadays the weighted pop-up quantization procedure, and also introduce this concept of ghost particles. So this is a nice paper really to see the genius of Feynman. Okay. Of course, Feynman tried to do this one loop computation. Nowadays, if you want to go to high loop gravity computation, it's very challenging. So, for example, even you consider a Feynman computation, a single three-point vertex would contain more than 100 terms, and just consider a high loop single diagram. For example, the five-loop single Feynman diagram would contain more than 10 to 30 terms. This is totally impossible using the most efficient computers nowadays. So, on the other hand, the high loop computation in gravity is also very important. Here I make two analogies between QCD and gravity. You know that QCD, there in the UV region is asymptotic 3, and this is where we need to do high precision productive computation to compare with like collided experiments. And of course, in the IR region, we have this non-productive regime, which people can do about lattice simulation. And in the gravity side, I mentioned this light event. So in this, in spiral region, people actually can do this particular computation using this post-Newton or post-Minkowski expansion. That is actually, people can do this quantum loop computation to take classical limit to extract this information. And in the merger this phase, people can do non-destructive, for example, numerical relativistic. From the previous talk, we know actually from this side, there's also a particular region to do this polynomial mode computation. Also, the high loop gravity computation is also very instrumental to understand the structure of UV divergence in gravity. For example, maybe some of you have heard that there's conjecture that this age of gravity may be UV finite. So, and to verify such of a UV enhancement symmetry for the UV structure, people really need to do these high loop computations to see whether this counter terms exist or not. So, apart from this superficial analogies, there's actually very deep connections between gravity and gauge series. So one example is nowadays a big subject about this so-called holography. This is basically means that high dimensional gravity is equivalent, is due to a gauge theory, which is linked in a boundary, this curved space. And another relation is so-called double copy. Okay. So basically, this means that the gravity is related to two copies of Yang-Mills. And this will be the topic we will focus in this talk. I will explain more detail about this concept. So the double copy, roughly speaking, is a gravity quantity can be written as a square to Yang-Mills quantities. So if you think about the free theory, think about particles, this is not so strange. For example, Yang-Mills theory is a spin 1 particle. We have to combine two spin 1, we form a spin 2 particle. Okay. So, and also in the string picture, you have two open strings. If you sew them together, you form a closed string, which is actually carry this gravity modes. Okay. The non-trivial thing is whether it's true also when you turn on interactions. Okay. So this is the idea which is actually realized back in the 1985. Kawai, Llewellyn, and Henry, they actually, by studying string amplitudes, they find that closed string amplitudes can be written as a product of two open string amplitudes. So these formulas are very complex. So you have a 4-point closed string, you have two 4-point open string. This is 5-point formulas. Okay. So if you take this low energy limit, take this string upper prime to be 0, you get the free theory amplitudes. The closed string becomes the gravitational amplitude, and the open string becomes the Yang-Mills amplitudes. So this is the precise equation relations that we formulate for the tree amplitude. Of course, all this framework works at tree level for general high points. However, whether this can be generalized to the quantum loop level, it hasn't been realized for many years. So the one generally new idea is so-called color time duality, which is introduced by Zwiffen, Roscoe, and Johansson in 2008. So basically, this picture is that if you consider a gauge theory amplitudes, once you realize this so-called color time duality on the gauge side, you can make a straightforward double copy to gauge the gravitational amplitudes. So this idea works not only at tree level, but also at quantum loop level. So let me give you some more details. So this is a framework for the scaling amplitudes. So we know amplitude is given, you can think about it in the Feynman diagrams. So you have an integral given by the Feynman diagrams. So you first, of course, you have a propagators, right? And in the numerators, in the gauge theory, you have this gauge color factors. Basically, it's given by the product of strata constants at ABC or the trace color factors. And you also have these kinematic factors, depends on the momentum of these polarizing vectors. Okay. And if these two factors satisfy same algebra relations. For the color factor, this is just the Jacobi, the algebra Jacobi relations. And if the kinematic factor satisfies this Jacobi one-to-one correspondence relations, you can directly make a replacement that remove this color factor and take another copy of kinematic factor. You immediately get the gravitational amplitudes. So this is a very simple operation. The non-trivial thing is you have to find the representation satisfy this relation. If you do a naive finite diagram computation, this relation is almost not true at all. Okay, but this conjecture claims that there exists a representation that this duality can be made manifest. For example, to consider this 4.3 amplitudes. Okay, so this is I should emphasize this. The diagram you should consider are cubic diagrams. So for the 4 point, you have this STV channel, 3 cubic diagrams. So the propagator and the color factor are basically fixed by topology. For example, the S channel color factor is just two strong constant time together. And CSCTCU satisfy the Jacobi relation. The real non-trivial thing here is that the numerator should satisfy this dual Jacobi relations. This is the thing that we have to try to construct. Once you have this duality, you get the gravitational amplitudes very straightforward. Any questions so far? Okay, good. So, this duality is quite non-trivial in the sense that color degree freedom is a gauge symmetry. Right? It's an internal symmetry, while the kinematic factor relating to the space-time symmetry. So these two symmetries are actually quite different from each other. So this is the non-trivial thing of this duality that at tree level we have a proof, but it's still nowadays still a conjecture. And look up is still conjecture. So to realize this double property, you see that the key part is to realize this cyclic duality, color duality. And for this duality, you only need to focus on the gauge theory side, right? Everything you just realize this symmetry for your Yang-Mills theory. So this gives you a strategy that by studying the simpler gauge theory, you may understand this far more complicated gravitational theory. That's a bonus that we could make from this duality. Okay. So now I will give you some more details. How do we compute this cyclic dual representations? It's not technical, but I hope I will give you a general picture how this is done. So first we assume there is a duality. Okay. Even though this is conjecture, we assume it's true. And we want to construct a compiling ansatz for the loop integral. You have propagators, you have a color factor and numerator factors. The non-trivial thing is you don't know what the numerator factor looks like. This color factor and propagator are just determined by the topology, by a diagram. However, if you impose a duality, you see the numerator factor are highly constrained already by this duality. It's an input duality. So this you will have a very compact ansatz. And it only depends on a few linear some linear three parameters in this integrand. I will also give you some more concrete example very soon. So then you have this ansatz. How do you fix this ansatz? I mean, there are some three parameters, or you guarantee this ansatz is a correct physical answer. Right? So this is where the utility cost plays a role. This is a modern on-shell amplitude method. The idea is actually like the optical theorem, you apply the utility property. If your integrand satisfies all possible cards, namely your integrand, all the residue property are correct and manifest its physical requirements, this is guaranteed to be a physical answer. Okay. And to check these cards, basically you just compare your answers by a product of three amplitudes. So on the right-hand side, this answer is no. On the left-hand side, you have the answers depends linearly on a set of three parameters. So mathematically, basically, it's just solving a linear algebra problems. The technical part is not so important, but basically you have a very systematic way to do this computation. And it's a linear algebra problem that we need to solve. However, you can also see the challenge here. This equation does not necessarily have a solution because we have a conjecture, right? So the difficulty here is that it's actually not known whether the solution exists. People have tried to compute some very high loop amplitudes in this very supersymmetric theory, the maximum supersymmetric amplitude supermills. For example, for the for loop 4-point amplitudes and the 5 loop pseudo-quantum form factors and up to 4 loop these 3-point form factors. So I will take an example of these 4 loop 3-point form factors. You can write down all the trivalent graphs. In this 4 loop example, you have more than 200 trivalent diagrams. Okay, and now we impose this color command duality, and it turns out that you only need to focus on 4 numerators, 4 diagrams. The reason is because you have these dual juxtapositions. Given these 4 numerators, you can generate the numerators of all other diagrams. Okay. So this is where this color command duality plays a non-trivial role. And then, since we only need to focus on these 4 diagrams, the answers for the numerators, you only also need to know for these 4 diagrams. I will also give you a complete number of the parameters here. Each of them contains about a few hundreds. So this for loop problems, non-trivial for loop problems, only contains about less than 2,000 parameters. Okay. It's a linear problem involving less than 2,000 parameters. And given these answers, now you can check the entire class. Okay. These are just the 3 amplitudes. By comparing these answers, you can solve the fixes to these 3 parameters, but you find that there are still more than 133 parameters left. Okay, but these 3 parameters, because it satisfies all entire class, you can view it as the gauge parameters. If you simplify your integrand or further do some integrand reduction, all these parameters actually cancel. Okay. The physical answer doesn't depend on this track. The non-trivial thing is that for this for loop form factor, you can find this solution. And you can here is a list for this up to for loop computation. You can see if you're just doing a naive computation for this cubic graphs, the number of graphs growing unfactorial. It's growing very fast. But the planar masters grows very slow. Even for the two loop order, you only need to deal with these 4 diagrams that I mentioned here. And you also find that up to 4 loop, it always has a solution. So although we haven't tried for the 5 loop, it looks high promising this strategy will work actually. Of course, in the realistic world, we don't have a symmetry. Right? How does this strategy work for the pure Yang theory, for example? This has to be very, very challenging. For non-supersymmetric Yang theory, even these 2 loop examples are very few. The only known 2 loop examples are these 2 loop 4 group amplitudes and with a particular all plus holistic configurations. This solution has been known by 3 groups more than 10 years ago. And there's another example, this 2 loop 5 points with all plus holistic. It's back to 2015. And if you consider generic, this D-dimension kinematics including all felicities, it's still not known nowadays. And so the difficulty is that it's not trivial to find the solution. So when you don't find a solution, it's not saying your solutions, what can you do? First, maybe your answers is too small. Then you try to enlarge the answers. But for example, in this 5-point 2 loop example, they have to make answers up to the loop momentum to the 12th power. You know, if you do a finite diagonal permutation, it's only the 7th power. So you have to increase a huge number of terms in this construction. Or if you consider this generic kinematics for the 4-point case, maybe you can give up these global sticky relations. Actually, in the 2015 groups, they have tried another strategy. They try to make answers for all topologies, and by only imposing this sticky duality on cars. So this all these strategies actually it's hard to generalize to high loop or high bound case because this increase your answers very fast. You give us the advantage of doing this global sticky duality by reducing to a very small set of master diagrams. Any questions? Okay. So now we come to the third part of this the new strategy we have tried to introduce. So the idea is that we introduce a new strategy by allowing a deformation. So we know that if you're just using the naive construction, this small n1, probably you will not find a solution. It fails. Then maybe you give up or you enlarge answers, increasing the complexity very much. The strategy here that we still want to take the minimum answers and take the efficiency of this strategy by introducing a very small deformation. So this little n1 and that one I will introduce next, give you more details what they are. So let's first review this part. Just suppose we don't introduce this deformation, what will happen? Okay. This is the standard construction. So the two loop 4-point, this amplitude contains these 14 triwritten diagrams that you need to consider. Okay. Then, if you impose these color kinetic dualities, I said the power of this duality is that it reduces number of diagrams significantly to a very small set of master topologies. So in this case, it turns out that you only need to care about these two master topologies. And all other numerators are determined by these two numerators through a certain dual Jacobi relations. So next you only need to make answers for these two master topologies. Okay. So what does this numerator looks like? It's just the polynomials of these Lorentz products. These P are momentums, epsilons are Brownian vectors. Okay. So the answers we make for these two numerators are about 20,000. Okay. Then you can impose a symmetry, the graph automorphism, respect to the symmetry graph, for example, the flip symmetry, or this kind of diagonal flip symmetry. You reduce the parameters to only about 1400. So next, given these answers, you impose your unitary cards. As I said, once your answers satisfy all unitary cards, it's guaranteed to be a finite answer. Your job is done. However, in this case, you find that these two cards, they are easily parsed. However, this ladder type two cards, it fails. What does it mean? This means that if you consider this traditional strategy, make a minimum answers, you don't have a solution. It cannot be a physical answer. So then what's the way out? So in the Driven, they take an alternative strategy by making answers for all these 14 diagrams. Okay. For each numerator, you have answers. So you basically give up this offshore duality relations. So the starting point, you would have 120,000 parameters, and your final answer have more than 6,000 degree freedoms left, free parameters. It's hard to see the water structure you have here. So we make a small progress, try to keep this offshore global city duality as much as possible by introducing a small deformation here to make these cards work. So how do we do that? We know the problem type in this class, right? Then we select a topology that only affect this double class, let have two double class. And you find that only 6 of them are related to these two double class. Okay. So the deformation that we made, we ask a deformation only make for these 6 topologies. Okay. And furthermore, we also ask this deformation satisfy a dual geometry relation. That means we don't need to make answers for all these 6 topologies. We only make deformation for a single one. This we call the master topology for the deformation. Okay. So once we know this deformation, we know all other deformations. So this is like an iterative structure. For the leap N1, you have this equation. You only care about 2 topologies. For this deformation, you also only care about very few topologies. Okay. So the next strategy is you see whether this construction works. So we since we only need to focus on these topologies, we also need to make answers for this deformed master numerator. There are some technical details here. I think I don't need to mention it here. You can classify according to different tensor structures. And anyway, so you find that the deformation that you need to do, for example, for this epsilon dot epsilon tensor structure, you only need to add 1 terms. Okay. For the other part, it's also a single, it's 1 term plus another terms. And finally, this deformation, this is the order deformation you need to know. It's only a 6 line expression. And I will make a comparison why this is so simple in a few slides. So basically now you have a solution that contains this deformation. You can still keep this N1 here. Okay. So you need to know these 2 master topologies and all others are known, but just without deformation, this doesn't work. But if you add these terms, by only consider these deformed topologies, now they combine together and make it a nice story. And all you only need to know is these 2 numerators plus this single deformed numerators. Why this is simple? We can see this deformation structure is only a 6 line expression. How about this little N1 here? This is the assay-based numerator in the text file. It's 1.4 megabytes. Okay. So this is, I cannot show you in a single screen. It's a very quick expression. Okay, but this is very typical for a 2-loop computation. If you do a Feynman diagram, it's much larger. However, it seems that by only adding a 6 line terms, everything makes nicely. Okay. The upshot is how can we know this in advance? We don't know yet. We find this single piece by the construction. And we have also performed several checks and solutions, like it passed all D-dimensional planar or non-planar cards. It satisfies all CK duality on cards. So our expression can be made double copy directly. So this is a necessary condition. Even we said we make a deformation that it doesn't satisfy the global offshore CK, but it satisfies CK on every cards. So this means that it also satisfies the gravitational amplitude on cards. It's a double copy giving the gravitational amplitudes. And also there are some other checks that free parameter cancels. It satisfies the correct IR Cardano formula, etc. Okay. So now I come to the summary of an outlook. So in this talk, I gave you the idea that the gauge and gravity theory are related by this double copy idea. And to understand this double copy or to implement this idea, actually you need to study your gauge theory side. And you need to achieve this color chimeric duality for your Yang-Mills theory. And normally this color chimeric duality is actually generally difficult to realize. And in this work, we introducing this idea of deformation. This may be a generic strategy to solve it. And as a comparison, the number of parameters here, if you don't using deformation, you have this more than 100,000 parameters. Our starting point is only 2 masters and 20,000. And in particular, your final answer depends on some free parameters because you have both this beta N1 and the delta 1. This result would have a much ugly result. You have a lots of number of free parameters. You don't need to do how to do it. And in this case, your structure is much simpler. You only have 200 free parameters. It would be interesting to be explored in this results, what kind of hidden structure you may have. So this provides hopefully a new strategy to apply city duality and double copies. And of course, the question is that why this deformation, at least in this example, why is it so simple? It's only a 6-line expression. And to test this strategy, we have also worked out a high-loop example that would be the 3-loop pseudo-quantum form factor in pure Yang-Mills. So this would be the first 3-loop non-symmetric example that we apply this kind of city duality ideas. And this is some details. You actually have a similar simplicity here. In this case, 3 cards failed. 3 cards failed. However, all the deformation you need to make is only for a single topology. The deformation is still relatively simple here. And of course, can we go into for example, high loop or high quantum case, for example, towards a 3 loop, this non-supersymmetric gravity. If we can do this Yang-Mills theory in 3 loop, we can make a double copy to get a 3 loop gravitational results. I think this is your have never been computed yet. And also, are there any underlying structure for this deformation, or for example, any algebraic structure for them? I think we probably we would need to know more data about this. And okay, I will stop here. Thank you for attention.
Very naive one. Suppose one day you prove that in fact gravity is the square of the Yang-Mills field. Completely. Exactly, so mathematical. What would be the good of that, considering that we cannot solve QCD, so we probably cannot solve quantum gravity as well?
Yeah, that would be the it's a hard question. So far, as I said, at 3 level, we have a certain constructural rule for that. We can always do this, and to really make connection, people have tried to whether we can formulate this double copy picture in terms of Lagrangian. You know, the Einstein Lagrangian is very different. So I think that one of the motivation is that since the Yang-Mills is well understood and is renomable, maybe this can if we can really have some fundamental interpretation why it's true at quantum level, we can actually understand quantum gravity.
So you were talking more about pure gravity, right?
My hope is to understand the pure gravity.
Yes.
Yeah.
So I wonder if you include matter, can you use this technique? Or...
Yes. So to give you an example, for example, only sports Yang-Mills for this mismatch, a double copy will give you only space supergravity. And actually, I was a bit cheating here. So if we make a double copy of pure Yang-Mills, we don't actually get the pure gravity. It's gravity coupled with the Beam field and the related field. So to get this Einstein gravity, you still have an extra step whether you can project this Beam field or the related field.
But if you have a pure Yang-Mills, you're saying you get gravity plus something else.
Yes.
But this something else is not necessarily everything which you can include.
Right. Probably then you can modify you have different type of Yang-Mills here. You can have less mathematical tools with Yang-Mills, but to Yang-Mills, you get, for example, maybe H supergravity. Right. So this kind of problem. Actually, from the morning talk, I'm thinking about what's the, you have this quadratic gravitational, which is renormalizable. What will be the Yang theory? Like you can make a double copy to that gravity. Maybe some high gravity Yang. I don't know whether in the weak theory, but I think that's definitely an interesting question to think about.
What was the same question?
Hi, Professor. I have a question. Here you discussed the gay and the gay series and gravity series are related by the double copy. I want to ask, can we create identically a gay series for gravity just as the electromagnetic use the U1 symmetry to create elementary fields? Can we also find a gay symmetry to create the gravity?
I think your question is whether we can double copy U1 theory.
Double copy U1.
When we start from the U1 theory, electromagnetic theory make a double copy of what that's all, right? That's all. So yeah, here is actually, if you consider all the entities I'm talking about, we need to have this geography identity. So actually, this is work only for Yang theory. That's for the case. You need this nonlinear interactions. But actually, the double copy actually works also for the classical solutions. For example, we know that black holes, strata black hole or Kerr black hole, if you're using the Kerr-Shilton metric, it actually can be made as a double copy of some Coulomb charge particle classical solution in electromagnetic. In that case, actually, you have a U1 classical solution make a double copy to get a black hole solution. For the amplitudes.
Thank you.
I should mention that let's say author is also experts.
Okay, can you apply also this interesting deformation technique just the string amplitudes, like if you take open string and yeah, I mean if you can comment about this in that.
I probably so far haven't idea to mention. I mean the KLQ relation works for string amplitudes, but in that case the double copy is a different structure. It's not based on color mathematics. I think so far advanced knowledge people have. Because string you don't have this nice color cubic diagram structure.
And you can put the terms back to length.
Yeah, I think that's interesting. I don't have a concrete thing.
Okay, first maybe a remark why do you need what helpful, how helpful will it be to have each theory squared with gravity? It's been already helpful because numerators that are linear. This is for your
question.
It's already been helpful in these particular calculations because if the numerator has a power n in momentum, then in gauge theory, then in corresponding gravity, it happens squared, and the complexity of a polynomial of degree twice as high as the other polynomial is always. Is it actually like no? Well, it's a big. It's practical. Yeah.
Practical. Use is clear, but what's in
yes.
That's my point. You know, if you look at computation of way beyond the part that we don't understand completely, they may be you don't get there.
But actually, I have a question now on the specifics.
Okay.
So your deformation, could you point out how the answers of the deformation it looks like compared to the answers of the original solution that failed? Do you have more momentum? Like powers of momentum? Did you have to include more powers of momentum?
No. It's all minimum answers. It's just a polynomials with lowest power of momentum.
So with the same powers that you would expect in a normal answer?
Yeah, because the price that we pay compared to the euro, if you add this deformation, it doesn't satisfy the
you relax. Yeah, you relax.
Yes. So that's a reaction.
All kinds. Okay, thanks.
So that's second house view again. Okay, so our last speaker is from UFT and going to talk about modality on gravitational EFTs.
So I'm very happy to be here and thanks for the invitation. So my talk will be, so I will still use scattering amplitude, but I'm basically doing something called bootstrap, which I will make later in the next slide. So normally in the standard textbook, when people introduce EFT, it is often emphasized that in EFT you have decoupling. Okay, you have UV scale and you integrate out this heavy particles, and then this heavy UV physics will be decoupled from the low energy. You only care about the operators. You should write down all possible operators, and you have a lot of so-called Wilson coefficients, and you go with that. Okay. Sometimes in this approach, it's implied that these Wilson coefficients can be anything. Okay. But I think thanks early 2000. After the swap idea, also in the range discussing popularity of swap land, people probably have already realized that that's actually not the whole story. There's actually a lot of UV and RR mixing in the theory. Even you integrate out the high energy physics, but still this high energy degrees freedom will have important imprint in the low energy. Okay, for example, if you do not, even if you do not know the UV theory, but you assume that the UV theory specifies causality and unitarity, you can derive a very strong bound on the low energy EFT coefficients, and these bounds are called positivity bounds or causality bounds. By the sound of it, it is a bootstrap, right? Bootstrap means you start from very simple things and then derive things which you deduce generically. For example, you can apply the positivity bond or causality bond in so-called standard model EFT. So standard model EFT is the theory of the standard model, but including high order operators, because we haven't observed anything at their LHC. So nowadays, a very popular approach is that you write down all possible operators beyond the renormalizable operators we have tested so far. And in that way, we don't have to rely on model building. We just test all the Wilson coefficients of this standard model EFT. And if you apply the leading positivity bound for so-called vector boson scattering, that is, you only scatter the vector bosons at the low energy in the snare model, you found that you will have very strong constraints on the parameter space. For example, for this VBS process, it's less than 1% of the total parameter space is consistent with the so-called positivity bound. Okay. And so, for example, in the 2D subspace, these are the experimental bounds, but positivity bound basically tells you that the EFT, the standard model EFT, which is consistent with the healthy Wilsonian UV condition, must be living in this wedge. Okay. From the low energy point of view, you don't there's no, you can't see any, reasons why these regions are not viable. So the tool we use to derive the positive bound is something called dispersion relation. It's a very old tool. People have used this in the 1960s when arithmetic program was in its early days and in its high day. So to derive the dispersion relation, we basically rely on the fact that the scattering amplitude when and analytically extended to the complex plane is analytical. So the only singularity you have is when, for example, when you fix P in the complex S plane, the only singularities are the ones you already observed in the low energy fields. You have poles or branch cut from loops. And the reason why this bond are for the causality bond, sometimes positivity bond, in this talk I will take them interchangeably. Sometimes they mean different things, but in this talk they mean the same thing. Okay, it's because causality implies analyticity. There's no regular proof of this except for some special cases, but generally people believe this should not be true. Okay, so to derive the dispersion relation, for example, you fix P and you do torches, you do normal things in the complex analysis. You do a contour on very close to the center of the zero, which is when the energy S is very small, and then you can blow up. And then you use for the force bound and the SU crossing symmetry, you can derive so-called drive subjective dispersion relation. So the IR unique connection or mixing is reflected in this simple relation. So on the right hand side, so S prime goes from lambda squared to infinity. Lambda squared is the cutoff of the theory. So we don't know the form of this imagined part of the amplitude because it's built above the cutoff. Okay, but we will assume that this amplitude satisfies unitarity. So we have a generalized optical theorem or optical theorem, from the unitarity. In particular, this guy, for the forward scattering, this guy is positive. That's the normal optical theorem. But we have more, we can do partial wave expansion, and then we have a series of positivity conditions. On the left-hand side, S and P can be very small, can be in the energy range of the EFT. So we can approximate this side with the EFT amplitude. So this dispersion relation connects the EFT amplitude and the IR amplitude. Okay, that's basically the only information tools we will use. Okay, sorry, that's not exactly true. In the previous, in deriving the previous dispersion relation, we only use the fact that the amplitude is SU crossing symmetry. Okay, for the single scalar fields, we know that it has triple crossing symmetry. We haven't used this equality yet. So it's only very recently we realized that in order to get the most stronger bond, you should enclose this equality. That will give you some extra dispersion relations, and this dispersion relation sum to zero, so therefore the null constraints. Okay, with this information added, then we can for the single scalar case, at least for the case of the case when the in IR the scalar field is weakly coupled, we can just prove that all the Wilson coefficients are order 1. Okay, this is not a surprising. I mean, this is usually what people have been doing EFT for a long time. It's just the reason we can prove that they have to be order 1 because we have calculated the exact bound or for this all of these coefficients. Now we can apply this bound to some simple models. In cosmology, we have a lot of scalars. Sometimes it's just one scalar. For example, in the discussion of dark energy, the condensity model is all usually used. And if we can have a decoupling limit for the theory, that means you should characterize the theory such that the decoupling limit that the graphon exchange does not contribute significantly. Then you can use the result of the previous slide on this condensity model, and you will find that some of the generic models or specific models are consistent with positive bound. Some of them are either severely restricted or ruled out by the positive bound. For example, so for the default theorem, you can rule out if you also impose the condition of that the speed of the gravitational wave is close to 1, then you can rule out this model completely. This rule out is in the sense that the positive bound constrains the cutoff of the theory to be very close to the mass of the theory. So there are some regions that you can set the positive bound in this default theory, but the problem is that in that ELT, the cutoff is very close to the mass of the scalar. That means this scalar ELT is not really a valid or very healthy, useful ELT. You can also apply the same bound to the first original beyond condensity model. The result is similar. Okay, so people have worked out quite a few models for these two-sided bonds. For example, for the scalar field, after our work, people have almost obtained this bond analytically, or you can use so-called for this metric experimentation to get all of these results confirmed, what we have done here. And people have also started to apply this bond for multi-field series. For example, people have applied the bond for the gravitational series. And in the following talk, I will talk about our work. It's actually last year's work that we applied this bond for the scalar tensor theory. That means in the previous application of the bond, we did that in the decoupling limit. We neglected the effects of the gravity. But now, in many cases, for example, if you want to test, gravity in the strong gravity regime, gravity is essential in the story. So that's also the motivation of doing this bond, because we have tested the gravity in the solar system and on small scale or large scales, and typically we get a very consistent result with general relativity, but we haven't tested gravity in the strong. We have just started to test the gravity in the strong gravity regime, and you can add the higher derivative terms for the pure gravity case. Another model which people often look at is that you add a new degrees of freedom. For example, a scalar field in the model. You talk about the scalar tensor theory. So the strategy is that you write down all possible operators consistent with the symmetry of the model, which is just the different orders in invariance, and with some extra degrees of freedom. So why is this model interesting? I mean, for me, one interesting aspect of this model is that they can give you Harry black hole solutions. Okay, for example, if you add the linear phi and the Gauss-Bonnet coupling, you will get Harry solution. Okay, so this coupling in some sense is the leading corrections to the Einstein gravity if you have some extra degrees of freedom, right? So there's a lot of no-care theorems, involving scalar field, but from the EFT point of view, Harry solutions are generic, because even if you include the leading ones with the coupling to the scalar, you will have Harry solutions. Also, another this has been mentioned earlier today, is that people talk about the so-called the spontaneous civilization. Okay, you can if you have some more generic couplings between the curvature and the scale field, you can have some in some circumstances with Harris solutions, and in other situations you have a normal GR solution. Okay. So to derive the bound, again, we need to use the dispersion relations. So for the graphic case, the dispersion relation obviously is much more complicated because now we have to expand the expand the imaginary part of the amplitude with the so-called Wigner image space. Okay, but that's just algebraic complicity. Okay, the real problem of this gravitational possibility bound is the existence of the T-channel pole. Okay, because of the existence of the T-channel pole, we can't expand the both sides of the dispersion relation in terms of S and P. We can only expand that in terms of the S. Okay, and so the summation of T here is going infinity. Okay, but to get the possibility bound, we want to access the region when T is close to the cutoff. So we cannot directly use this this kind of dispersion relation. So the first problem that this summation goes to infinity is easy to solve. You just use the crossing symmetry and some other, you do another x derivative on this guy and use those 3 times subjective dispersion relation. You can easily get rid of this high order p derivatives. Okay. Then, if you want to constrain the leading field order dispersion relation, it's just that you have to deal with more this kind of some rules. But that still doesn't address the real problem that there's still 1 over t term here. Okay. Without this 1 over t term, the possibility bound is that this number is positive. But in presence of this two-channel pole, this guy is no longer positive. Okay. So that's a difficulty. So to solve to make use of this kind of dispersion relation, a method has devised that you should use so-called functional optimization. Okay, instead of optimizing over a few decision variables, now you optimizing a series of functions. Okay, and you also want to sum up all important constraints, UV constant, with the impact parameter formulation. So what is functional optimization? So this is the so we should choose a series of decision variables which are functions of p. The p is basically p is basically p squared is p. P is the moment transfer in the scattering amplitude. So if we can find a series of this kind of wave function such that on the right hand side, in the integrand of the right hand side is positive definite, then you can derive a series of constraints on the Wilson coefficients. Okay. Now, how do we impose this condition? You realize that there's generalized optic theorem, so you basically impose. You use the fact that the optic theorem basically has the imaginary part of the partial wave amplitude is a positive definite matrix. Okay, compared to the single scalar case, the difference for that case is just a positive number, but for this case, the important thing is that the positive matrix. So we impose a series of matrices being positive. To get the bound, numerical bound, you want to sum of all possible constraints. Okay, the constraint space is enumerated by the UV spins. So this is basically the spin of the UV particle, and or under the UV mass scale. This is basically the scale of the UV particle above the lambda squared. Okay. Ideally, we want to sum all of them, do that analytically, but in practice we can't, right? We have to do it numerically, and we have to truncate. Okay, we have to truncate. We should truncate away some parameters, constant, and only keep as much as possible the important ones. So for the finite L spin and the mass scale, that's easy. You just use the constraints I mentioned. For the other scale, you have to use a serious approximation to simplify. Otherwise, it's very slow. It's a big system. It's quite difficult to do it numerically, unlike the single scalar case. And for the large L and mu case and the mu region, you have to use this impact parameter formulation. Another thing is that because there's not really a four-dimensional graviton scattering, because there's actually IR divergence. So that divergence actually also factors in our possibility bound because of the T-channel pole. That's also related to the T-channel pole, right? So because of the T-channel pole, you will have to impose some IR cutoff for this kind of bounds. So in the end, with all this setup, we can plot some bounds on the parameters. Okay. So this is the Lagrangian, and these are the coefficients. These are the coefficients we want to constrain. Okay. The important one important thing I don't show here is that all the bounds actually depend on this D5 to 4 coupling. Okay. So some of them depend on this coupling sensitivity, but some of them does not depend on this coupling sensitivity. Okay. So in many of the plots, I will list the different values of this alpha and say what the results are. Okay. Phenomenologically, we are interested in this coupling. That's the coupling that gives rise to Harry black hole solution, and that is the one of the leading Einstein pure gravity correction to Einstein's gravity. Okay. Now, with the previous setup, you can find that the square of these parameters must be in this region. Okay.
The other couplings are free.
We are agnostic about other couplings. Okay, so we don't assume anything for the other couplings. Now we use all the optimization machinery to constrain these two parameters. So in this sense, this is the projection of the very high dimensional bounds to the plane, right? We choose the largest possible allowed parameter region. If you assume a value for other couplings, then this plot will be shrinking significantly. Okay, this is the largest allowed parameter to these two parameters. And you found that there are two kinks, okay, for this plot. One here and another one here. If you listen to the talks about the icing model, safety bootstrap icing model, they first identified icing model as the kink of something, and then they improve the bound, and then they shrink the bound to the kink. Okay. Now they can constrain the icing model to a very, very small region. Okay. For us, we can't do that because it's S metrics, and S metrics generally nowadays we know that they allow a very large number of possibilities. Okay, but with the possibility bound, you can probe what kind of theory this. We don't exactly know what these two things correspond to, underlying theory. But with the possibility bound, it's easy to give some first hints of what these things are. Okay. For example, we can set different UV spins. We can neglect some spins and then see what happens. If we neglect the spin 1 scalar, if we do not allow any UV scalars, then we found that the bond will be shrink to this region. So this region, for this region, so if the parameter space is in here, that means in the UV, there must be some UV scalars. Okay, the same applies for this massive spin 2. So if the parameter is in this a point in this region, that means there must be some spin 2 particles in the UV. Okay, obviously you can also have high spins, right? In the case of the string theory, you have limited number of higher spins. And we can also easily, from this formula, it's also easy to say that if there are only very high spin, if the UV theory only has a spin higher than 5, then there will be no EFT left. Okay, the whole region will be shrinking to 0. Okay, in cosmology, sometimes people use a lot of quantum theory. Okay, for example, when they discuss about the scalarization, people only focus on this model. Okay, set all the high order coefficients to 0. Strictly speaking, this is actually not correct, because strictly, if you really set all the high order parameters to 0, then you will find that you will find inconsistency. Okay, it's not allowed by the dispersion relation. And you can the way to look at the reason is that if you do that, then the dispersion relation basically imposes the constraints that the Planck scale has to go to infinity. Okay, you can generally, if you set some of the parameter space, parameter relationship to 0 will lead to all these spectral functions to be 0, then you will have inconsistency. Okay. Of course, you say that generically, when people talk about this model, we are not actually setting all the high order parameters to 0. We are basically saying that high order parameters are small. Okay. In that case, you found that actually imposes the fact that the high order parameters being small actually imposes very strong constraints on the low order parameters. Okay, as you shrink the high order parameter, you found that the bound will shrink to a very small region. Now, you can also constrain the bound for these two terms. I mean, so this one gives you the Harris solution. When you talk about if you want to for the spontaneous scalarization, you basically set this to be 0 or very small, and you allow this number to be very big. Okay. Our result shows that this is actually quite a generic result, because the allowed parameter region for this parameter is much larger than this one. Okay, in a sense, the so-called scalarization is natural in terms of the parameter allowed region of parameter space from the view of the rebound. Okay, so finally, let me summarize a take-home message about the parameter space of the gravitational EFT. So this is a slide I steal from Simon Caron. Okay, so they work about the bound for pure gravity, okay, for pure gravity EFT. Okay, in that theory, you obviously have the Planck scale, and you also have the cutoff. Okay, how do we do the power counting for this kind of EFT? Okay, without gravity, we know there's a 9th dimensional analysis you can learn from the EFT textbook, but with gravity, no, it's not known. Okay. So this guy showed that, okay, in the literature, you found a lot of power counting for different power counting for different ways. For example, we can restrict to Minkowski space and do Paul counting the same as the 9-dimensional matrices, and you come up with this Paul counting. Okay, you found that actually some of these regions are not really allowed. Okay, sometimes people say, oh, we have the leading Einstein here, and we just put the cutoff here, and that's our Paul counting. Okay, this is too restrictive because string theory already violates this. Possibility bound tells you that the right way to do Paul counting for pure gravity is that you should have n Planck squared in front of everything, and then you square all high order fractions to Einstein gravity with the cutoff. Okay, this is the most allowed parameter region for your EFT. Now, what if we add matter fields like a scalar tensor theory? Okay. In this case, it's not so simple anymore because you also have the scalar fields. What we found is that what you can do, okay, obviously we calculated the parameter space, right? We have the numerical methods to calculate that. But what we found is that you can actually extract the allowed region from some, after doing the numerical analysis, we found that you can extract the allowed region from this simple analysis. Okay, you first extract the hierarchy between lambda and which is cutoff and Planck scale for these spectrum functions. For the pure, so the plus means the the positive helicity plus 2 helicity, and minus means minus 2 helicity. Okay, 0 means there's a scalar degree freedom. Okay, for the scalar degree freedom, you have different way of assigning the hierarchy between for the spectrum function. You can either specify one or first order of this hierarchy. Once you do that, then you can basically plug this into the dispersion relation, survey all possible available dispersion relation, and then basically power times the allowed region of the parameter space from these dispersion relations. Okay, you still have to do some work. It's not that you can list this power counting directly, but this is usually it can be done in a few minutes. Okay, slightly more than a few minutes. For the lowest order scalar tensor theory, for example, we found that the power counting should obey this law. Okay, so you have your cutoff expression for derivative, cutoff expression for the Einstein Hilbert for Riemann tensor, and for the scalar field, and then you will have some extra factor of m1 divided by lambda. Okay, and this is integer. The integer is decided by the power of the power of the scalar field in the series. Take the lower divided by 2 and take the lower integer of that number. Obviously, this does not apply for the high orders, but for the Lagrangian we listed out here, it applies. Okay. So positive bound or quadratic bound are the UV unitarity conditions passed down by to the IR by the dispersion relations. So we have calculated the positive bound for the scalar tensor theory, and this is another example of a multitude scalar tensor theory which confirms the previous result that all the parameter space of the EFT should be order 1 with some strictly normalized units, and we found that so for the scalarization, it's natural in terms of allowed parameter space. We also found a way to power count gravitational EFTs with matter fields. Okay, that's all. Thank you.
It's not clear to me why would you be interested in constraining operators which have been without a time again calculated. I mean, the development terminal, we know for 20 years that it induces superluminal motion, tachyons, very motion at the ground. And 3 years ago, that the terminal has been completely ruled out by double pulsar observation. So, I think insisting on something that you already know that violates everything possible on a cosmological background and even around the quantum object.
So
another thing, yeah. So I have a second part of this comment. Another thing that would be more interesting to do would be, since it is model, you naturally use the frequency dependent dispersion relation for the graviton. One can place constraints using waveforms. In ESA, we do better for precisely for this type of government recommendations, and the precision of an observatory is enough to warrant post-uniform expansion up to order 2.5. So you can really make precise information gravitational waves on spectral relation for this type. And that is something that is relatively new and maybe more interested, but again, removing terms, living terms of problem.
So I think a lot of people would disagree with you that the linear coupling with corresponding and ruled out. I think you mentioned that the superluminality is essentially the Pacific bound. The fact that yes, it's Pacific bound basically relies on causality. Causality means that there should be no observable superluminality. You can also derive the boundary exactly the same way for that. Actually, we have we are writing up a paper to use the causality in the within the EFT to bound these parameters. There's a lot of I mean, eventually you still just impose some constraints, right? You cannot causality does not
for that on the cosmological background, the simple as that, and you have a superluminal motor in
depends on how you define the superluminal, right? There are a lot of ways to misuse the fact that there's a lot of misconception about how to use superluminality, impose causality, conditions within the DFT. Okay.
And we were not doing ADFT, we were just measuring the group velocity of
There are a lot of misconceptions, unfortunately.
Well, you can call it misconception, but at least they should compare with those results because I've been in for decades. And you cannot just straight away what people already know from full pulsars, which is something more recent. It's much more sophisticated, and they use precisely galvanic couple of therapy.
I have one question. So there is a recent paper by David Kaplan, Sujit Rajendran, and Francesca Serra with a very provocative title, "Wrong Science Are All Right." Whereas it writes that it's all okay to have wrong science from the point of view of Lausanne.
I probably haven't read that paper. Do you know what they are considering?
Well, they basically claim the same thing what we claimed with Slava and Geneva before. That if you take a theory which allows for superluminal propagation, it doesn't mean that you violate your value. Because in most cases.
Yeah. That's the point I was making. I mean, regarding the previous question. So there's a lot of misconception. I think nowadays, within the EFT, the right conception is that you should impose a so-called IR causality, right? So you should compute. Okay, there's one way to impose the causality is that you impose so you calculate the Shapiro time delay, and the right condition you impose is that you subject to the GR part of the contribution. You don't have to do that, but that you get a weak bound. You want to get a stronger bound, you subject with the GR part of the Shapiro time delay, you get the pure EFT part of the time delay, and you impose that this time delay is
It's not resolved.
can be resolved, right? That means the frequency of this, it's should not be greater than the inverse of the energy of the frequency of this, the energy you are scheduling onto
Well,
the thing.
to be honest, like it's an even more complicated question, because if you send a pulse will have to be in front velocity. This is front velocity is not described by your real EFT, right? In that case, what will happen is this wave cannot arrive before the front. So therefore, there will be any time delay or time advance, because the pulse propagates faster than light in IR. The more propagate faster than that is
Even if you use the frequency of the wave you are sending in, and you use this input so-called IR causality, then you do not find inconsistencies to these models.
Oh, sure, but I mean, that's the point is we do not get this pulse, right? If physically there is something that we can break it in IR.
Yeah.
But in UV, you say that the dispersion relation goes to normal one, standard one, then the front of this pulse will arrive to you with the speed of light. It will not be faster than the light, because the front is high frequency noise. And whether it's really describable with all the approach in that sense.
But that's difficult to be imposed, right? I don't know exactly what they mentioned about this, but I think, this is consistent with what I'm saying, that you should, careful about imposing the causalities within the EFT.
You should start.
Yeah.
Thanks.
Can I have a question? Can I ask a question about spin certain rule? I will be confused about the result that it is this time. What does it mean that vacuum could be no higher than spin 5 particles in UV? And how does it fit with the string theory?
So right here, that if you only allow, so you have a UV spin, right? If you only allow the UV spin to be greater than 5, then the bound shrinks to 0.
Yeah, but I see that in string theory, you normally have all like.
You also have a lower spin. If you add L equals to 3, 0, 1, 2, then you are consistent. But if you say that in the UV theory, I don't have any spin lower than 5, then you do not have a consistent EFT. You will have
We only want to have lower spins in addition to that.
Sorry.
You mean that you need to have lower spins in addition to high spins? You cannot
you can not only have a spin higher than 5, but without 0 or 1, 2, 3, 4.
Thanks. So we will have first thanks Tonyo again. Here probably we need some more discussion, so let's not end the discussion session. So if anyone have questions to any of the speaker today, you can also give it to ask.
Yeah, speaking about the misconceptions of how to check it out, it's not a negative or positive, it's not a systematic to consider schedule and day. Here you have very high complete construction, the whole of the system. You have a lot of parameters, you have not just the single extraction. So even if you render, you not per se and it's sufficient to make a conclusion about causality. And as a second point, the mathematical parameter does not just about causality, but generates instabilities at cosmological scale. and weak vector. I mean, you cannot just make interpretation of vector. Those are the instabilities where canonical solution background is just a block. So you cannot get rid of that. Even if you fix the causality part, then you still have this. You can not really leave up in practice where classical instability.
Yeah, I'm not aware of. Yeah. I'm not aware of the cosmological perturbation theory of this model. I know that people have studied the black hole stability and they found no problem for this. Okay. But for the cosmological perturbation, I don't know. But the context people are talking about these models the scale is not cosmological, right? People are talking about whether you can have these models close to the black hole, whether you can see these things close to the black hole, right? But even for the cosmological perturbation theory, in EFT you have a lot of available diversity. That's usually okay because depends on the scale of this instability. If this scale is close to the cutoff of the model, then you don't have any problem for that, right? So I don't know the exact context of this, the paper you were mentioning, or the work someone else did, but yeah, for the black hole, I think that's a different scale.
So that one has all the different way. All right, thank you. Without any more questions. Okay, so it's not then that's how we do it.
If you want to take them, I can try tomorrow at 9. Okay? You remember, tomorrow we start at 9. So in the surprise, we're going to get that.